Hello, and welcome to the Sleepy Voyager. If you enjoy drifting off to wonder, mystery, and gentle science, please tap subscribe and turn on the bell. It helps this sleepy channel float a little farther each night, and it tells me to keep making quiet documentaries just like this one. Now settle in, breathe slowly, and let's follow a visitor from the deep dark. 3i Atlas. A new object showed up in wide-field sky images as a small, faint dot that moved a little between pictures taken on different nights. Survey telescopes scan the sky regularly, so computers compare fresh images to older ones and mark anything that changes. When the software flagged this dot, astronomers checked it carefully to rule out things like camera noise, a passing satellite, or a known asteroid. The dot kept showing up. It moved in a steady way that matched a real object in space. Teams at other observatories pointed their instruments to the same place and confirmed it. With a few nights of data, they could just track how fast it was going and in what direction, and they could start to work out its path. To understand whether something belongs to our solar system, scientists try to fit its path to an orbit around the Sun. Most asteroids and comets follow ellipses, which look like stretched circles. The shape is described by a number called the eccentricity. If the number is less than 1, the object is bound to the Sun. If the number is greater than 1, the path is open, like a one-time swing by. After careful measurements, the eccentricity for this object came out greater than 1. Its speed at a large distance from the Sun, called the hyperbolic excess speed, was also higher than what you would expect for something that formed here. Together, those clues said this was not a regular member of our solar system. It was passing through from somewhere else in the galaxy. Because it is the third such visitor we have found, it received an interstellar designation with the number 3, and it is commonly referred to as 3i Atlas. Once the path was clear, observers tried to learn what the object was made of. If sunlight warms ices on a comet, those ices can turn into gas and carry dust away, making a fuzzy cloud called a coma. That cloud often makes the object brighten and can change its motion slightly because tiny jets act like miniature thrusters. If there is no coma, the object may be more like an asteroid, which reflects sunlight but does not shed gas. Telescopes took images and spectra, splitting the light into colours to look for signs of gases or minerals. They also watched how the brightness changed over hours and days. A steady rhythm can show how fast the object spins. A big rise and fall can point to a long, thin shape, while small changes suggest a more rounded body. These are simple, indirect clues that help build a picture when the object is too small and too far to resolve. Because the object is faint, many telescopes have to work together. Some watch in visible light, some in infrared, and some in ultraviolet. Each part of the spectrum tells us something different. Infrared can hint at temperature. Visible light shows general brightness and colour. Ultraviolet can reveal certain gases if they are present. Observers share data, so the combined set covers more nights and a wider range of wavelengths. This teamwork reduces errors and helps separate real behaviour from noise in the measurements. Another important step is to remove the effect of Earth's own motion. As our planet orbits the Sun, nearby objects appear to shift position slightly, a bit like how your thumb seems to move if you hold it up and switch which eye is open. This is called parallax. Careful calculations subtract Earth's motion so we can see the object's true path. After this correction, 3i Atlas still followed a hyperbolic trajectory. That confirmed the interstellar nature of the visitor. As days pass, the geometry between the Sun, Earth, and the object changes. Sometimes this makes it easier to see, sometimes it makes it harder. Observers plan their schedules to catch the times when the object is highest in the sky and far from the glare of the moon. They also try to get data before dawn or after dusk when the air is most stable, because a steadier atmosphere gives sharper measurements. If the object brightens, more small telescopes can join in. If it fades, only larger telescopes can still collect useful light. This is normal for faint targets. People naturally ask if 3i Atlas is a comet or an asteroid. The answer depends on whether it shows gas and dust activity, and on how its brightness behaves as it approaches and leaves the Sun. Some interstellar objects have looked more like comets with clear Comean tails. Others have behaved oddly and challenged simple labels. Scientists try to avoid jumping to conclusions. They collect enough data to test different explanations and see which one fits the best. It is fine to say we don't know yet while the measurements continue, and it's common to update an idea when new observations arrive. When we say an object breaks the rules, we usually mean that our simple model is missing a piece. For example, if gravity alone does not explain the motion, tiny amounts of outgassing can add a small extra push. If the brightness does not change in a normal way, the surface might be covered with dark material, or the shape might be unusual, or the spin might be wobbling. These are not magic answers. They are practical possibilities that can be tested with more data. Over time, better models include these small effects and become the new, improved rules. Interstellar objects are valuable because they bring samples of other star systems to us. Even without picking up a physical piece, the light they reflect and emit carries chemical fingerprints. Spectra can show water, carbon-bearing compounds, or other ices and minerals. Colours can hint at space weathering, which happens when cosmic rays and sunlight slowly change surfaces over millions of years. By comparing these clues to what we know about comets and asteroids from our own system, we learn how similar or different other planetary systems might be. It is also helpful to place 3I Atlas in context. The first object we recognised as interstellar was 1I/Oumuamua, which behaved in surprising ways and sparked many debates. The second was 2I/Borisov, which looked much more like a typical comet, with a clear coma and tail. Each new example adds to a small but growing set, and patterns may appear as the sample grows. A pattern might be, most interstellar objects are comet-like, or it might be, they show a wide range of behaviour. Either way, the data will guide the conclusion rather than the other way around. Everything about this process depends on clear records. Observers note the time, the telescope, the filter, the exposure length and the conditions. They calibrate their images against known stars to make sure the brightness scale is correct. They share their measurements with central databases so anyone can attempt an orbit fit or a light curve study. When teams publish results, they include uncertainties, which tell readers how confident they are in each number. Uncertainties are not flaws, they are part of honest measurement and help others judge how strong a claim is. For people who are new to this topic, it helps to remember one simple idea. Space is big, and objects can be thrown out of their home systems by gravity interactions. Over very long times, some of those objects will pass near our Sun. Most will be too faint to notice, but once in a while, one will be bright enough and well placed for our telescopes to see. When that happens, we can learn about distant places without going there. That is the main reason 3I Atlas matters. It is a passing sample from somewhere else, and by paying attention to it, we practice and improve the way we study the universe. As observations continue, the path prediction gets tighter, the spin state becomes clearer, and any signs of gas or dust are either confirmed or ruled out. If the object stays quiet, that tells us something. If it becomes active near the Sun, that tells us something else. Either way, the information is useful. The goal is not to force the object into a label, but to describe what it actually does step by step in a way that anyone can check. This careful approach is slow but reliable, and it is how we turn a moving dot on a screen into real knowledge about a real visitor from beyond our solar system. Imagine the space around the Sun is not as empty, but as a very thin river of particles and light always flowing outward. This steady flow is called the solar wind, and it carries the Sun's magnetic field with it in a spiral pattern shaped by the Sun's rotation. When a small object passes through this stream, an asteroid, a comet or an interstellar visitor, its path is guided mostly by gravity, but not only by gravity. Sunlight itself pushes a little, like a constant breeze on a leaf. Charged particles in the solar wind can touch the object's surface, build up a tiny electrical charge and nudge dust off it. All of these effects are small compared to the Sun's pull, yet with precise measurements they show up as gentle, real changes to the route the object takes through space. Astronomers describe the path using math that predicts where the object should be at any given time. If gravity from the Sun and planets were the whole story, the predicted positions and the measured positions would match within normal errors. When the view do not, researchers look for non-gravitational effects. One common cause is outgassing. Sunlight warms pockets of ice, turning them into gas that escapes as a jet. Each jet is like a tiny thruster, adding or subtracting a bit of speed in a specific direction. If the jets are stronger on the sunlit side, the push tends to be away from the Sun. If the object is tumbling, the push can change direction over hours, creating a complex pattern. To capture this, orbital models add 3 small parameters, often called radial, transverse and normal accelerations, that represent steady components of this extra force. If including those terms makes the residuals, the differences between prediction and observation, shrink, you know you are on the right track. Light pressure is another steady influence. Photons carry momentum, and when they hit a surface and reflect or are absorbed, they transfer that momentum. The result is a continuous gentle push away from the Sun. How strong it is depends on the object's area to mass ratio. A fluffy, low-density body or one with a sail-like shape feels a larger effect than a compact, heavy rock the same size. Observationally, this shows up as a small acceleration that scales with the inverse square of the distance from the Sun, the same way sunlight fades with distance. When analysts fit the trajectory and see an outward push that follows this rule, radiation pressure becomes a reasonable explanation to test against the data. The solar wind's magnetic field can matter too, especially for very fine dust around the object. As gas escapes, it can drag dust grains with it. Those grains can become electrically charged by sunlight and by the wind itself. Charged dust interacts with the magnetic field lines that sweep past like invisible threads, which can help shape a faint tail and can remove momentum in directions that pure gravity would not. Even when the object is too faint for us to see a clear tail, the interaction region can slightly alter how escaping material leaves, which in turn feeds back into how the nucleus moves. This is why spectra and deep images are valuable, though. They do not only tell us what the object is made of, they help us understand whether the environment around it is adding forces we need to include. There are also thermal effects. If one side of the object warms up and then re-emits that heat a little later as it rotates, the re-radiated infrared light can act like a tiny rocket exhaust. This is related to the Yarkovsky effect, well known for small asteroids. For an icy body with active jets, gas forces usually dominate. For a quiet rocky body, thermal re-radiation can matter more. The challenge is that we rarely know the exact shape, spin axis, or surface properties, so the modelling becomes a careful game of ruling in what is consistent with the data and ruling out what is not. Light curves, how brightness changes over time, tell us about rotation. Colours and infrared measurements hint at surface texture. Together, they narrow the range of possible non-gravitational forces that could be at work. In practice, all of these influences are measured through timing and angles. An observatory records the object's position against background stars at a precise moment. Dozens of observatories do this on different nights. The result is a long list of time-stamped positions. Computer fits an orbit to that list. Then it checks the residuals. If the residuals cluster randomly and are small, the model is good. If they drift in a pattern, always a little sunward, or always a little ahead of where gravity says it should be, the team adds a simple non-gravitational term and tries again. The goal is not to force the data to agree, but to find the simplest physical cause that explains the disagreement. Once a good fit exists, it can predict the future path more reliably, which helps everyone plan observations. Planetary gravity also leaves fingerprints. As the object passes near a planet, even at a large distance, it receives a gentle tug that slightly bends its trajectory. These perturbations are expected and built into good models using high-precision ephemerides for the planets. The art is in separating these known pulls from the smaller, continuous pushes of sunlight and outgassing. When analysts say tiny course changes don't add up, they usually mean that after accounting for planetary tugs and measurement errors, there remains a small, consistent acceleration that needs a physical explanation. Often, the simplest answer is either outgassing or radiation pressure, but the data must decide. The solar wind also shapes the object's immediate neighbourhood, especially if gas is present. As neutral atoms stream off the surface, some collide with solar wind protons and swap charges. This charge exchange can create fast neutral atoms and slower ions, modifying the local flow. The interplanetary magnetic field can drape around the outflow region, forming something like a temporary induced magnetosphere. Instruments sensitive to certain emission lines can see this process indirectly as faint glows. While this does not shove the nucleus strongly, it affects how material leaves, and therefore how much reactive force the jets deliver. If jets prefer certain weak spots or fractures, the thrust becomes directional and time-dependent, adding wobble to the already small push. Because the pushes and pulls depend on distance from the Sun, their relative importance changes along the journey. Far out, gravity dominates and non-gravitational effects are usually below the noise. As the object approaches the Sun, sunlight grows stronger by the inverse square law. Weak jets can turn on. Dust can be lofted more easily. Thermal re-radiation increases. The path that looked purely gravitational at first can start to deviate in a measurable way. This is why early and late observations both matter. They set a baseline and then show the onset of extra effects. A good habit is to refit the orbit as new data comes in, rather than assume the early solution will hold unchanged. Sometimes the best clue comes from contradictions. For example, if spectra show little or no gas but the trajectory still demands an outward push, then radiation pressure or thermal effects climb to the top of the list. If the object's brightness varies in a way that suggests a very elongated shape, then a larger area to mass ratio becomes plausible, which again makes radiation pressure a better candidate. If neither gas nor a high area to mass ratio seems likely, analysts re-examine systematics. Are star catalogues, timing, or atmospheric effects biasing the measurements? This loop of proposed test revise is normal and healthy. It is how a mystery force becomes either a measurement correction or a real, quantified physical effect. The environment through which the object moves is itself structured. The solar wind is faster and thinner at some times, slower and denser at others. Coronal holes and solar storms change its character, and the magnetic field lines bend and twist with the Sun's 27-day rotation. If an object passes through a region of enhanced solar wind or a sector boundary where the magnetic polarity flips, its coma and tail, if present, can react quickly while the nucleus responds only through whatever thrust those changes produce. Coordinating space weather data with comet observations helps connect sudden changes in appearance or jet behaviour to known solar conditions, which tightens the physical story and avoids attributing every wiggle to something exotic. All of this attention to tiny forces has a clear purpose: better predictions and better physics. Accurate paths let observers point telescopes at the right place at the right time, especially when the object is faint and observing windows are short. Good physical models teach us how small bodies behave when they are warmed, spun, and sandblasted by sunlight and star wind. Each interstellar object adds a new test case because its surface may have been processed under different cosmic ray levels and different chemistry long before it ever met our Sun. By tracking how its trail bends and brightens through the solar wind, we learn not only where it will be tomorrow, but also which small, steady forces sculpt small worlds everywhere. In simple terms, think of gravity as the main road, and everything else, sunlight pressure, tiny gas jets, thermal re-radiation, and the touch of the solar wind, as gentle side breezes. Most of the time the car stays on the road, but if you watch closely over a long distance, you can see the car drift a little to the side in a way that repeats with the shape of the land and the weather. Measuring that drift and matching it to the known breezes is what turns a line across the sky into an explanation you can trust. The trail through star wind is not a sign that the rules are broken. It is the sign that the rules include small terms that only careful watching can reveal. When astronomers study a small object far away, the first and most basic thing they measure is how bright it looks. That simple number changes over time, and those changes are full of clues. If the object were a smooth ball that didn't spin and didn't shed any dust or gas, its brightness would rise and fall in a very predictable way as it moved closer to and farther from the Sun and Earth. In reality, the curve of brightness over time, the light curve, often refuses to be that simple. It wiggles, it pulses, it dips when it should rise, and it flares when it should be calm. None of this means the laws of physics are broken. It means the object is reminding us that shape, spin, surface texture, and tiny activity all matter, and those details are layered together in the light we receive. One of the biggest players is rotation. Most small bodies spin and very few are close to perfect spheres. Imagine a potato-shaped rock turning in space. As it spins, sometimes the long side faces us and reflects more sunlight. Sometimes the short end faces us and reflects less. That alone can make the brightness go up and down in a steady rhythm like a lighthouse. But there is a twist. Some objects don't spin neatly around one axis. They tumble, a motion called wobble, or non-principal axis rotation. When that happens, the rhythm beats in overlapping patterns, so the light curve looks like two or more drums playing at once. To a graph, it becomes a complex wave that is hard to fit with just a single period. Astronomers then collect more nights of data to tease apart the timing and decide whether there is a clean spin or a true tumble hiding in the noise. Distance and geometry matter too. The Sun, the object, and Earth form a triangle that changes shape every day. The angle at the object between the Sun and Earth is called the phase angle. At small phase angles, when we look almost straight back along the sunlight, the surface can brighten quickly due to an effect called opposition surge, a simple way of saying that shadows on the surface shrink and more light is sent back toward us. At larger phase angles, when we see the object more from the side, the same surface sends less light our way. If you only watched the distance and ignored this viewing angle, you could think the object was misbehaving when it was actually just changing how it presents itself to us. So observers always correct for both distance and phase when they try to decide whether something unusual is happening. Surface properties are another layer. Dark, soot-like coatings made of carbon-rich material can lower the overall brightness, while fresher, cleaner ice or rock reflects more light. Rough, powdery surfaces scatter light differently than smooth, compact ones. Grain size in dust also matters. Very small grains can forward scatter sunlight, meaning they send extra light in the direction the light is already travelling. If a thin cloud of those grains forms around the object, a coma, then at certain angles the coma can make the whole thing look brighter than expected, even if the solid core hasn't changed at all. That can trick simple models into thinking the object got bigger or closer or spun a different way, when the real change was in the dust around it. Activity from warmed ices can complicate the things further. When sunlight reaches pockets of ice, the ice turns to gas and lifts tiny dust grains into space. Sometimes this happens smoothly, but sometimes it happens in spurts, like a kettle that rattles now and then. These small outbursts can make the brightness jump for a few hours and then settle back down. If several jets come and go on different parts of the surface, the overall light curve becomes a blend of rotation, geometry, and short-lived flares. Because most interstellar visitors are faint, we often see only the combined effect, not each jet by itself. That is why repeated observing nights are so valuable. They let scientists separate regular patterns, like spin, from one-time events, like a brief puff of gas. Colour provides extra clues. By measuring brightness through different filters, roughly blue, auroras, green and red, plus infrared, astronomers can see whether the object is getting redder or bluer as it brightens. If the brightening comes mostly from dust, the colours may tilt in a way that suggests lots of tiny grains. If the brightening is just the solid surface turning to face us differently, the colours may stay more stable. Sometimes colours redden with phase angle, meaning the object looks redder when viewed more from the side. That effect, called phase reddening, tells us about surface roughness and grain size. None of these shifts are huge, but together they act like different instruments in a band, each adding a piece to the full song. Thermal glow, heat re-radiated as infrared light, joins the SORI near the sun. Even if an object is too cold to feel warm to us, it still absorbs sunlight and sends that energy back out at longer wavelengths. By comparing reflected sunlight visible light to this gentle heat infrared, scientists estimate how big the object might be and how efficiently its surface holds and releases heat, a property called thermal inertia. A surface that heats and cools quickly like loose dust will behave differently from a surface that holds heat, like rock or ice with a crust. If the thermal glow rises without a matching rise in reflected light, the object may have become warmer without shedding extra dust. If both rise together, activity may be involved. Measurement details can create illusions too, so careful calibration is everything. Telescopes must correct for atmospheric conditions, stray moonlight, and the exact sensitivity of their detectors. They compare the object's brightness to nearby standard stars with well-known values to make sure each night's numbers line up with the next. If a background star passes close to the object on the sky and blends with it in the image, the object can appear to brighten briefly, then dim once the star moves away. Automated checks and human review look for those situations, so they are not mistaken for real changes. With all these pieces in play, how do astronomers decide whether the light is behaving? They build a simple baseline model first. How bright should the object be just from distance and a standard phase function, a rule of thumb curve, for how brightness changes with angle? Then they layer on rotation by fitting a repeating pattern. If the fit still struggles, they test a 2-period model for a tumble. If activity is suspected, they look for colour changes and for brightness that scales the way dust scattering should. If forward scattering by dust is likely, the brightness should rise faster than expected at certain angles. Each improvement is checked against the data, and the idea with the fewest assumptions that matches best is preferred. Polarized light adds a bonus test. Sunlight waves can align more in one direction after bouncing off certain surfaces. Measuring this polarization helps tell smooth from rough and large grains from tiny grains. A rise in polarization with phase angle is typical for dusty comets and rough surfaces, while flatter behavior can hint at different textures. Again, no single test gives all the answers, but together they narrow the options in a reliable way. When people hear the light doesn't behave, they might imagine a dramatic, unexplained effect. What it usually means is that a very simple model, smooth ball, steady spin, no dust, cannot explain the detailed curve. The fix is rarely a wild idea. It is often a more realistic shape, a less than neat spin, a small coma that turns on and off, or a surface that scatters light in a slightly different way than average. Interstellar visitors make this detective work even more interesting, because their surfaces may have been altered by eons of deep space radiation in ways we do not see on most local comets and asteroids. So when 3i Atlas brightens oddly and then relaxes, or when its light curve refuses to lock into one tidy period, the message is not physics is broken, but look closer. Shape, spin, dust, and viewing angle are sharing the stage, and our job is to listen carefully until the pattern makes sense. When scientists say an object's path misses a beat, they mean that precise measurements of its position don't line up perfectly with the path predicted by gravity alone. Gravity is still in charge. No one is throwing out Newton or Einstein, but tiny extra pushes or pulls are showing up in the data. The way we find those small effects is straightforward. We collect many time-stamped sky positions from observatories around the world. We compute the best gravitational orbit using the sun and planets and sometimes big asteroids as the sources of pull, and then we inspect the residuals, the differences between where the model says the object should be and where telescopes actually saw it. If the residuals look random and small, the model is fine. If they drift in a pattern, always a little sunward or always a little outward, or consistently ahead of schedule, then gravity is missing a beat, and we add simple physically motivated terms to capture what's going on. The most common extra term for small icy bodies is outgassing. Sunlight warms ices trapped just beneath the surface. Those ices turn to gas, and the gas vents through cracks, carrying dust with it. Every vent is a tiny thruster. If vents are mostly on the sunward side, the net pushes away from the sun. If the object is tumbling, the direction of the net push can change with time, sometimes strengthening, sometimes weakening, depending on which regions are illuminated. Orbit models usually start with a simple version of this effect. 3 constant components of acceleration: radial, toward, away from the sun; transverse, along the direction of motion; and normal, out of the orbital plane. Fitting those 3 numbers often removes the patterned residuals dramatically. If that works, we have not discovered new physics. We have identified a small rocket effect and measured its strength. Sunlight itself adds another gentle, steady push called radiation pressure. Photons carry momentum. When they hit a surface and are absorbed or reflected, they transfer that momentum to the object. The magnitude of this push scales with the object's area-to-mass ratio and drops with the square of the distance from the sun. That means fluffy, low-density objects, or highly elongated, thin shapes, feel radiation pressure more strongly than compact, massive ones. In the data, radiation pressure looks like a constant outward acceleration that grows as the object nears the sun. If spectra and images show little or no gas, but the orbit still demands a small outward push, radiation pressure becomes the leading explanation to test. Thermal re-radiation can matter as well, especially for rocky or inactive small bodies. An object absorbs sunlight on its day side and re-emits that energy as heat, mostly in the infrared, with a slight delay as the surface warms and cools. That anisotropic directional emission acts like a tiny thrust. This is related to the Yarkovsky effect. If the spin axis is tilted and the surface has some thermal inertia, the net thrust can systematically add or subtract a tiny bit of speed along the orbit over months to years. For an icy jetting body, gas forces usually dominate. For a quiet, warmer one, thermal thrust can be the main non-gravitational term. Distinguishing the two requires combining visible light photometry, colours, and infrared measurements to estimate size, spin, and surface texture. Before declaring any extra force, modelers also make sure the gravity part is as accurate as it can be. High-precision planetary ephemerides place the sun, planets, and large moons precisely. General relativistic corrections are included for motion near the sun. Light time delays, the time photons take to reach us, and stellar aberration, apparent sky shift due to Earth's motion, are accounted for. The reference frame is tied to modern star catalogues, ideally Gaia, to debias historic astrometry. Even small things like the sun's slight ablateness, tides from Jupiter and Saturn, and the tugs of a few massive asteroids can be considered if the data are precise enough and the time span is long. Tightening each of these pieces trims away false residuals so that any remaining pattern is much more likely to be real physics on the small body itself. Measurement systematics can mimic physics, so they're checked carefully. A background star blending with the target can make a fake brightening and bias the centroid. Thin clouds can shift measured positions subtly. Timing stamps can be off by seconds if observatory clocks drift. Using multiple sites, multiple instruments, and independent reductions helps reveal these issues, because a real physical effect should appear coherently across different datasets, while local systematics usually do not. When a suspicious batch is found, it is either corrected or down-weighted, so it does not dominate the fit. Once non-gravitational parameters are added, the fitting process uses weighted least squares or similar methods to adjust all unknowns together. 6 orbital elements plus the extra accelerations, sometimes plus a spin state or activity law that changes with distance from the sun. The result is a best fit set of numbers and a covariance matrix that shows how they correlate. Correlations matter. For example, a weak data arc can confuse a small outward push with a small change in eccentricity. That is why long-time coverage, before, during and after perihelion, is so valuable. It breaks degeneracies and makes the answer stable. To test robustness, analysts create clones of the orbit by sampling within the uncertainties and then propagate them forward and backward with and without the non-gravitational terms. If the clones without extra forces drift away from the observations, but the clones with them stay tight, the case is strong. Close planetary passes get special attention. Even a distant pass by Jupiter can bend a trajectory a little. And if the bending happens during a stretch with sparse observations, it can look like an offset that later gets misattributed to jets or radiation pressure. Good dynamical models march the orbit through all significant gravitational encounters using up-to-date ephemerades, so that what remains to be explained is genuinely small-body physics rather than missed planetary tugs. In rare cases, radar ranging or a stellar occultation, when the object briefly blocks a star, adds sharp constraints on position, distance, or size that lock down the fit even more tightly. If outgassing is the suspected cause, there is another cross-check. Activity seen in spectra or imaging near the times when the non-gravitational acceleration rises. Emission lines from common cometary species, a detectable coma, or a short dust tail all support the jet interpretation. If no gas is seen down to strong limits and the acceleration still looks like a clean inverse square push, the radiation pressure route stays favoured, which in turn implies a higher area to mass ratio and invites shape and density hypotheses consistent with the photometry. If there is modest gas but the direction of the acceleration seems odd, a complex rotation state could be steering the net jet thrust, which can be explored by fitting two rotational periods in the light curve or by testing simple spin models. A useful mental picture is a train on a very smooth track. Gravity lays the track. The train's wheels follow it exactly unless small side winds or engine puffs nudge it. Our measurements are like distant cameras snapping the train's position every few minutes. If the track model is perfect and there's no wind, the snapshots line up. If a consistent breeze blows from the same side, each picture will be a few centimetres off in that direction. We don't conclude the rails are wrong, we add a wind term and see the mismatch disappear. The key is that the correction is small, steady and physically sensible. There are also cases where the mystery force fades after cleaning the dataset, upgrading star catalogues or extending the observation arc. That outcome is good science too. It means we've traded an exciting but flimsy claim for a quieter, more reliable orbit. Conversely, when the extra acceleration persists through all checks, we quantify it, report its uncertainty, and explore the physical implications cautiously. How much mass loss would be needed to create the measured thrust if it is jets? What area to mass ratio would reproduce the same effect if it is radiation pressure? Are those numbers consistent with the object's brightness, colours, and thermal behaviour? Framing the answers this way keeps the explanation anchored to observations rather than speculation. Modellers also watch how the required acceleration evolves with heliocentric distance. Jet-driven thrust usually ramps up strongly as sunlight intensifies and then fades again. Radiation pressure follows a simple 1/r² law. Thermal thrust can depend on spin and season. Fitting a distance-dependent law rather than a flat constant often improves the match and adds physical meaning. If the law that best fits the data is the same law that describes sublimation of a likely ice, like water or carbon dioxide, that is another point in favour of the jet hypothesis. If the data prefer a pure one over a squared term with no colour or spectral signs of gas, the radiation pressure explanation grows more compelling. All of this careful work has two practical payoffs. First, better trajectory forecasts. When a target is faint and time on big telescopes is scarce, knowing exactly where to point and when can make the difference between a detection and a miss. Second, better physics of small bodies. The strengths and directions of non-gravitational forces teach us about surface cohesion, porosity, vent geometry, spin states, and even internal structure. Interstellar visitors are especially valuable test cases because their surfaces may have been altered by cosmic rays and cold for ages in ways we rarely see on local objects, so the balance of forces can look a little different. When gravity misses a beat and we add back the small notes, the song of the orbit becomes clear again. and each measured note tells us something real about the little world singing it. When a small icy body warms in sunlight, it can grow a fuzzy shell around itself called a coma. The coma is not fire, even though it glows. It is a cloud of very cold gas and dust that reflects sunlight and sometimes faintly fluoresces. Think of frost on a garage freezer door suddenly turning to vapor when the door is opened. On a comet or interstellar visitor, that door opening is sunrise, and the vapor is gas escaping from tiny pockets of ice just under the surface. As the gas leaves, it drags dust grains with it, and together they create the soft glow that telescopes record. This process can be smooth, like a quiet kettle, or it can sputter and pulse if the ice is patchy. The cracks are narrow, or the sunlight changes quickly as the object spins. Different ices wake up at different temperatures. Water ice needs the surface to get relatively warm before it turns to gas, so it tends to be active closer to the sun. Carbon dioxide, CO2, and carbon monoxide, CO, can sublimate, turn straight from solid to gas, much farther out where it is still very cold. That means a coma can appear surprisingly early in the journey inward, long before water ice is involved. On an object that has spent ages in deep space, super volatile ices like CO can hide below the top layer and vent through cracks when even a small amount of sunlight arrives. If those cracks open on parts of the surface that roll into darkness, the gas may keep flowing for a while because the heat takes time to move out and because pressurized pockets don't close the instant the light switches off. This is one reason activity can seem to come from the night side. The energy and the gas are coming from just beneath the surface with a delay. The surface itself is rarely smooth. Ridges, pits, and cliffs can focus sunlight into small hot spots, even when the sun is low, and those shapes can also shade other areas for hours. Light that bounces from bright dust within the coma can softly illuminate nearby terrain, a kind of indirect lighting that helps keep gas flowing after local sunset. Warm rock or dust can re-radiate heat in the infrared, gently toasting nearby shadows. All of this makes activity patterns look counterintuitive at first glance. A jet can appear to be coming from darkness simply because the true heat source is a warm wall just out of view, or because the gas found a sideways path to a crack that opens into shade. When gas escapes, it expands quickly. Typical gas speeds are on the order of hundreds of meters per second to about a kilometer per second near the surface, slowing as the cloud spreads. Dust grains hitch a ride, but they are heavier relative to the push the gas gives them, so they take off more slowly and can fall back if they are big enough or if the gas is weak. Fine dust, microns across, can be lofted easily and fills the inner coma. Larger grains, millimeters or more, may arc out and then settle back down, smoothing slopes and building drifts. The balance between gas drag and the grain's weight and stickiness cohesion decides what escapes. This balance changes with sunlight, spin state, and even local texture, so the coma often looks lumpy or jetty rather than like a perfect sphere. Sunlight does two jobs at once. It warms and it pushes. Photons have momentum, so they impart a tiny shove to dust grains. Small grains feel that shove more strongly relative to their mass than big grains do. As a result, the dust in the coma starts to sort itself by size as it flows outward. Over time and distance, this sorting plus the steady outward push from sunlight forms the familiar tail that points generally away from the sun. If you could trace the dust paths, you would see families of curves that depend on grain size and release time. Professionals even have names for these map lines: synchrones for release times and syndines for grain sizes. For a faint interstellar visitor, we may not see a long showy tail, but the same physics still shapes the near object glow and can make one side brighter than the other. Gas adds its own light in a different way. Some molecules, like cyanogen, Cn, and fragments of carbon chains, C2, C3, absorb sunlight and then re-emit it at very specific colours. Under the right filters, these gases make the coma look like it has soft, coloured halos. Oxygen atoms freed from water can glow in forbidden lines that show up as faint red or green features in spectra. Ultraviolet observations can pick up hydroxyl, OH, a direct daughter of water, and thus give a measure of how much water is actually coming off. By comparing these gas signatures to the overall brightness, scientists can separate how much of the light is from dust and how much is from gas, and they can estimate production rates, the number of molecules being released every second. The strength of activity usually follows the amount of sunlight, which rises sharply as the object nears the sun. A common first rule is that gas and dust output scale like one divided by the distance squared, or even more steeply, but real surfaces often behave in steps. Quiet, then a threshold is reached, then a jump as a new patch starts venting. If an area is covered by a tough crust of processed material, it can block gas until cracks widen. Then the gas bursts through and the coma brightens. Later, the same area can choke as dust falls back and plugs the opening. This on-off pattern can make the light curve look spiky and can make jets appear to turn on near the day-night boundary, the terminator, which again may be mistaken for night-side activity unless the geometry is modelled carefully. Under the top layer, ice can exist in an amorphous form, disordered rather than crystalline. When amorphous ice slowly turns crystalline as it warms, it releases trapped gases and a bit of heat. That change can drive activity even without direct sunlight at that exact spot, because the transformation front can migrate downward like a slow wave. In plain terms, heat from earlier sunshine can keep working under the surface after sunset, providing power for jets that look like they come from darkness. In layered terrain, stronger ices, CO or CO2, deeper down can find paths to the surface where water ice near the top would not, so the fuel line is routed through whichever crack connects to open space, regardless of where the sun currently shines. Rotation ties everything together. As the object spins, a fixed vent traces a spiral in space, so a narrow jet can look like a corkscrew in long exposures. If several vents are active at once at different latitudes and longitudes, their spirals overlap, creating fans and streaks that change from night to night. A change in rotation rate, a spin up from jet torque, or a spin down as jets shift, will alter these patterns gradually. Careful time series of images allow teams to solve for the spin period and the orientation of the spin axis by watching these fans swing. If the same pattern repeats every so many hours, that time is the rotation period. If it drifts slowly, a wobble, tumbling may be present. To make sense of coma brightness in a standard way, comet researchers often use a quantity called AFREO. It combines the dust's reflectivity, A, the fraction of the field of view filled by dust F, and the radius of the aperture on the sky rho. AFR behaves roughly like a measure of how much dust is being produced, but it is fairly insensitive to distance and to the exact size of the telescope's measuring window, which makes it handy for comparing observations from different nights and different telescopes. If F rises as the object approaches the sun and then falls after perihelion, that's a classic dust activity profile. If it flatlines while gas lines rise, dust production is weak relative to gas. If it spikes in short bursts, outbursts are likely. Polarization, how the electric field of light is oriented after scattering, adds another diagnostic. Dust in the coma tends to polarize light in ways that depend on grain size and structure. By measuring polarization at different phase angles, observers can infer whether the dust is fluffy aggregates, compact grains, or a mix, and whether the coma is dominated by very fine particles or something coarser. Interstellar surfaces might produce dust with different textures than typical solar system comets, so a polarization curve that deviates from standard patterns is especially interesting and can hint at a different history of radiation exposure or chemistry. Even the surrounding space environment leaves its mark on the coma. The solar wind's magnetic field can drape around the outflowing gas, forming an induced magnetosphere for a time. Charge exchange between fast protons in the wind and neutral atoms from the coma can create energetic neutral atoms and slower pickup ions. These processes can subtly reshape the inner coma and tail, and if a solar storm passes by, the coma might react quickly. Bright knots, kinks in the tail, while the nucleus itself only responds indirectly through changes in jet thrust. Matching these sudden changes to solar wind data helps keep the physical picture grounded and avoids blaming every wiggle on exotic causes. Because activity nudges the nucleus, coma studies and orbit fitting go hand in hand. If the coma is strong and asymmetric, a net force will push the nucleus, and the non-gravitational terms in the orbit will grow. If the coma fades, those terms should relax. Coordinating photometry, brightness, spectroscopy, gas composition, and astrometry, precise positions, allows teams to check that the amount of jet thrust implied by the coma is consistent with the measured trajectory changes. When the numbers agree, confidence rises that the physical model, what ice is venting, where the vents are, how the spin is oriented, is on the right track. All of this can happen even when the object remains faint and only a little brighter than the background sky. The coma does not need to be dramatic to be informative. A barely detectable fuzz, a shallow increase in brightness at certain angles, a gentle colour shift toward red with phase angle, or a small rise in AFR can each be enough to say, gas is lifting dust here, or the dust grains are very small, or activity is dominated by a volatile that works in the cold. And when activity seems to come from the night side, the simplest testable ideas, thermal lag under the surface, indirect heating from nearby terrain, pressurized pockets venting through cracks that open into shadow, or super volatile ices that do not need much heat, explain it without rewriting physics. The coma is the visible conversation between sunlight and surface, and even when it looks like cold fire glowing in the dark, it is telling us, in steady measurable ways, exactly how a small world breathes. When we watch a small distant object brighten and dim over hours, the simplest explanation is rotation. As it turns, its cross-section toward us changes, so the amount of sunlight it reflects changes too. If the body were a perfect sphere with a uniform surface, the brightness would barely vary. Most small bodies aren't perfect spheres. They're elongated, lumpy, or even double-lobed, so their light curves rise and fall in a pattern that repeats with the spin. The height of that rise and fall, called the amplitude, tells us something about shape. A common first-order estimate uses the relation A approximately 2.5 log base 10 over divided by B, where A is the peak-to-peak amplitude in magnitudes and a /BA/B is the ratio of the long-to-short axis in the plane of the sky. An amplitude of 0.75 mag suggests A over B approximately 2A over B, approximately 2. 1.5 mag suggests A over B approximately 4A over B, approximately 4. But this estimate assumes we are viewing equator on, the surface reflects light in a typical way, and there is no dust coma adding extra glow. Change any of those and the same light curve can come from very different shapes. A clean rotation produces a single stable period. In practice, interstellar visitors are faint and data arrive in short nightly chunks separated by daylight and weather. So period finding needs careful math. Analysts often use Lomsgargle periodograms to search unevenly sampled data for repeating signals, then refine with phase dispersion minimization or template fitting. Aliases, false periods caused by regular gaps in time sampling, are common, especially near 24 hours or its fractions. To break aliases, teams combine data from widely separated longitudes so the sky never blinks, or they observe intensively across multiple rotations. Even then, the period you find from Earth is synodic, what you see from your moving vantage point. Converting to the true sidereal period requires accounting for how the viewing geometry changes as the object and Earth both move. Many small bodies don't spin about their principal axis at all, they tumble. In rigid body mechanics, this is non-principal axis, NPA, rotation, described by Euler's equations. Instead of one neatly repeating brightness pattern, you see two or more frequencies, a faster rotation about a body axis, and a slower precession of that axis around the total angular momentum vector. The light curve then looks like beats and drifts rather than a steady drum. Over weeks, peaks slide in phase, and the amplitude waxes and wanes. Modelling NPA rotation means fitting at least 2 periods in their coupling, which demands long, well-calibrated time series. Internal friction damps tumbling over time, but the damping timescale scales with size, spin rate and internal structure. For a porous, rigid object a few hundred meters across, damping can take years to millennia, so an interstellar object can plausibly arrive still in an excited state. Surface scattering laws complicate shape inferences. Real surfaces are neither perfect diffusers nor perfect mirrors. Photometric models like Lommel-Seeliger or Hapke attempt to capture how roughness, porosity and particle phase function change the way brightness depends on the phase angle, the sun-object-observer angle. At small phase angles you get an opposition surge, a sharp brightening as mutual shadows disappear, and coherent backscatter adds light. If you ignore this, you might mistake a geometry-driven surge for a shape effect. Likewise, strong forward scattering by fine dust in a thin coma can boost brightness when the phase angle grows, mimicking a larger projected area. Separating surface scattering from geometry requires multi-filter photometry across a range of phase angles, with coma contamination carefully modelled or subtracted. A powerful way to move beyond the simple axis ratio estimate is light curve inversion. Given many light curves taken at different viewing geometries, convex inversion algorithms recover a best fit spin state, period and pole direction, and a coarse convex shape model that reproduces the data. This works best when the aspect angle, our angle to the spin axis, changes significantly during the apparition. For interstellar targets, the geometry often changes quickly, which helps, but their faintness limits data quantity and quality. Pole solutions usually come in mirror pairs due to north-south ambiguity, and low phase angle coverage reduces uniqueness. Adding constraints, colours, thermal data, or even a single stellar occultation can collapse these degeneracies. Thermal infrared light curves add an independent line of evidence. As the body rotates, the warmest terrain sweeps in and out of view, producing a thermal light curve that can be offset, phase-lagged, from the visible light curve. The size of that lag and the amplitude inform the thermal inertia, how quickly the surface heats and cools. Low thermal inertia, fluffy regolith, gives strong day-night temperature contrasts and small phase lags. Higher inertia, rockier or ice-cemented, smooths them out. Thermophysical models combine shape as spin and thermal inertia to match both visible and IR data, refining size estimates and helping decide whether the visible amplitude is shape-driven or reflectance-driven. Spin doesn't have to be constant. Tiny torques can steadily change it. The YORP effect, a torque from an isotropic thermal re-radiation off an irregular body, can spin small asteroids up or down over years to decades. For active bodies, jet torques from outgassing can produce much faster changes. Observationally, a changing spin appears as a slow drift in the best fit period, p dot not equal to 0, or as evolving light curve amplitude and profile over weeks. Detecting p.p requires consistent calibration and enough time baseline to separate real drift from nightly systematics. If p dot is less than 0, spinning up, increased activity near perihelion is a usual suspect. If p dot is greater than 0, jets may be breaking the rotation, or YORP could be at work with the opposite sign depending on shape and pole. Some light curve shapes hint at binaries or contact binaries rather than single elongated bodies. Deep flat bottom minima or alternating high/low peaks can indicate mutual eclipses or two lobes presenting different areas. A peanut or bilobate body can mimic a large axis ratio in photometry without requiring an implausibly thin shard. Interstellar objects invite extra caution here, because small comae can round off minima and fill in eclipses, hiding binary signatures. Conversely, short-lived dust outbursts can create spurious peaks that resemble mutual events. Consistency across many rotations is the key test. Geometry-driven features repeat. Outbursts do not. Geometry can trick the eye even without dust. If we view near pole on, the projected area hardly changes with rotation, so a truly elongated body can look nearly constant in brightness. If we swing toward equator on later in the apparition, the amplitude grows, giving the false impression the body's stretched. This is why reporting the aspect angle, or at least modelling families of solutions across plausible pole orientations, is standard practice. Similarly, specular reflection, glints from smooth ice patches or aligned facets, can create sharp spikes at specific geometries, imitating extreme shapes. Multi-filter behaviour helps diagnose glints. They are typically more colour neutral and geometrically narrow than jet-driven brightenings. Coma contamination is a recurring challenge. A faint, nearly unresolved dust cloud adds a smooth pedestal of light that reduces the apparent amplitude and can change its phase dependence. Observers counter this by using small photometric apertures matched to the point spread function, subtracting a local sky annulus to remove diffuse flux, and checking whether amplitude grows when using tighter apertures, a sign that extended coma was diluting the variability. Spectroscopy taken close in time can place limits on gas species. If gas is present but amplitude remains high, jets are likely localized and the nucleus signature is still visible. If gas is absent and amplitude is low, a compact, possibly rounded nucleus becomes more likely, unless we are near pole on. From the physics side, rotation state ties directly to interior properties. A rigid body precesses and nutates according to its moments of inertia. Internal dissipation damps those motions at rates set by rigidity and quality factor QQ. Porous, rubble pile structures dissipate differently than monolithic ice rock. If we see rapid damping, tumbling fading into principal axis rotation within weeks, that hints at strong dissipation, or external torques changing the state. If tumbling persists, the interior may be stiff and cold. Jet torques can also move the spin axis, true polar wander, if vents are asymmetric and long-lived. Tracking subtle changes in light curve shape over the apparition can reveal such pole motion, which then feeds back into jet models and non-gravitational acceleration fits. On the data analysis side, practical details matter. Absolute calibration ties brightness to standard stars. Differential photometry reduces nightly transparency errors. Using Gaia star catalogues minimizes astrometric and photometric biases. Accounting for color terms between the object and comparison stars avoids artificial trends. Error bars should reflect scintillation noise, sky background, and systematics. Underestimating errors will overfit and produce spurious period precision. Window functions, the pattern of observation times, should be inspected so that strong aliases are recognized in the periodogram. Where possible, combining light curves from different telescopes requires zero-point offsets and filter transformations to a common system. When enough geometry is covered, even a single well-timed stellar occultation, where the object briefly blocks a star, can pin down an instantaneous silhouette and absolute size along one chord, anchoring the scale of shape models that photometry alone leaves relative. Radar would be ideal for shape, spin and surface roughness, but interstellar targets are generally too far and faint for current radar facilities. Thermal IR fills some of that gap by constraining effective size via emitted flux, especially when combined with a plausible range of albedos. The beaming parameter in thermal models captures surface roughness and anisotropy. Values significantly different from typical cometry surfaces would flag unusual texture. Putting it all together means treating the light curve as a layered signal. Baseline trends from changing distance and phase, periodic terms from rotation, 1 or 2 frequencies if tumbling, slow evolution from changing aspect and possible P.P, and non-periodic features from outbursts or observing artifacts. The safest interpretations are those that survive cross-checks across filters, apertures and nights, and that remain consistent with independent constraints from spectra, thermal data and dynamics. Under those conditions, what first looks like a dramatic illusion, a shard, a pancake, a rule-breaking spinel, usually resolves into a physically sensible combination of shape, spin state, surface scattering, and, if present, a small amount of dust that together write the brightness rhythm we see. Space is not silent in the way a vacuum chamber is silent. Around the sun, the solar wind streams outward as a thin plasma, electrons and protons carrying the sun's magnetic field wrapped into a rotating spiral. When that moving magnetized gas meets a small object that is shedding even a little neutral gas and dust, the region around the object turns into a laboratory for gentle electrical and magnetic effects. Sunlight knocks electrons off dust and rock by the photoelectric effect, leaving surfaces slightly positively charged. Electrons from the solar wind can also stick to grains and to the gas cloud, sometimes making parts of the environment go negative. These charges are tiny, but they matter, because plasma pays attention to even weak electric and magnetic fields. A dust grain tens of microns across can pick up enough charge that the Lorentz force, charge times velocity times magnetic field, bends its path a little, changing how it drifts away. The smallest grains, the ones most easily lofted by gas, are the ones most easily steered by the field, so they trace out structures that would never appear if gravity alone were in charge. As neutral atoms escape into the wind, some of them swap electrons with fast protons in a process called charge exchange. The result is a pickup ion, a formerly neutral atom that becomes an ion inside the flowing magnetic field. Newly born pickup ions start out moving slowly relative to the solar wind, so the magnetic field forces them into spiral paths gyromotion around the field lines. This streaming and spiraling can excite waves in the plasma, like ripples in a pond, but carried by electric and magnetic fields rather than water. The characteristic timescales depend on the gyro frequency, omega equals QB over m, which for a given species, say protons or oxygen ions, tells you how fast a particle circles a field line of strength BB. If the outflow is steady, the waves are steady hums. If the outflow sputters with jets, the waves come and go, matching the heartbeat of activity. Because the solar wind drags the interplanetary magnetic field past the object, those field lines can drape around the outflow region. Imagine streamers of ribbon wrapping around a rock in a river. If enough gas is present, the draping can form a boundary, an induced magnetosphere, where the flow is slowed and diverted. There is no solid magnetic shield like Earth's. Instead, the coma itself, by becoming ionized, builds a temporary obstacle that the wind must flow around. Inside this region, the magnetic field strength typically increases, directions swing, and the plasma density changes. Farther downstream, the flow rejoins and forms a comet-like tail in magnetic quantities as well as in dust, with field lines stretched out and sometimes reconnected in small magnetic islands. The electrons in the solar wind and in the ionized coma can support a different family of waves. Langmuir waves. These are high-frequency oscillations of electrons against a nearly stationary background of positive ions. The natural frequency for such oscillations, the plasma frequency, is Fp approximately 9 square root of Ne kilohertz, when the electron density Ne is in centimeters to the negative third. If the local electron density changes, because a jet turns on or because the wind compressor, the frequency of these waves shifts. Instruments sensitive to radio and plasma waves on spacecraft have heard these notes near comets before. Smooth hiss, punctuated by bursts when a jet wakes up or when a solar wind disturbance sweeps by. Even without a spacecraft nearby, ground-based radio telescopes can listen for certain species that fluoresce at radio wavelengths. The classic example is the 18-centimeter emission from the OH radical, a daughter of water. It is not a voice in the human sense, but it is a measurable radio signature that rises and falls with activity and with how the magnetic and radiation environment pump those molecules. Magnetism also whispers through polarization and alignment effects. Elongated dust grains that become slightly charged can align very weakly with the magnetic field as they drift, especially if they spin due to gas drag. Aligned grains scatter light in a way that can increase linear polarization along preferred directions. By mapping how polarization changes across the coma and tail, observers get a proxy for the local field geometry, much the way iron filings reveal the pattern around a bar magnet. Only here the filings are micron-sized grains, and the map is made from starlight filtered through them. If the polarization angle swings smoothly across the tail, that often signals field draping. If it kinks or forms bands, reconnection or waves may be passing through. Charging is a dynamic balance, not a fixed label. Sunlight strips electrons, the wind brings electrons. Secondary electrons are knocked out by energetic particles. Electrons reattach. The resulting surface potential on the nucleus and on dust grains tends to be a few volts positive near strong sunlight, and can dip toward negative in shadowed regions or during certain solar wind conditions. Those few volts are enough to alter whether fine dust sticks or lifts, because electrostatic forces act over tiny distances where gravity is weakest. On airless moons, these forces can loft grains in fountains at sunrise along crater rims. On a tiny active object, they can help decide which grains reseat on the surface and which join the coma, slightly biasing dust sizes and directions so that even the coma's texture is a magnetic and electric story. As neutral gas streams outward, solar ultraviolet light photoionizes a fraction of it, turning it into ions that are then picked up by the wind. The pickup process extracts momentum from the flow, effectively acting like a brake. In strong cases around big comae, the wind slows upstream of the nucleus, and a bow wave-like structure forms. In weaker cases, like a modest interstellar visitor, the slowdown is subtle but still measurable as a shift in wave power and field orientation if an instrument were present. Downstream, an ion tail forms that is distinct from the dust tail. It is narrower, often straighter, and points more directly along the anti-solar magnetic field direction rather than simply away from the sun. Even faint ion tails caught with deep narrowband imaging mark where the magnetic conveyor is carrying newly born ions away. Radio lines from molecules carry their own set of magnetic clues. The population of rotational energy levels in molecules like C, N, HCN, or OH depends on sunlight pumping and on collisions with electrons and ions. Changes in electron density, set by both outgassing and the impinging solar wind, alter line strengths and profiles. Broadening or small shifts can also hint at bulk outflow speeds. By tracking these lines over many nights, astronomers watch the ionization environment rise and fall, and sometimes catch brief enhancements when a correlating interaction region, a faster stream in the solar wind, sweeps past. If the line intensities and the non-gravitational accelerations change together, that flags a common driver. More gas means both more radio emission and more jet thrust. If radio lines jump without a matching thrust change, the likely culprit is a solar wind or magnetic event that altered ionization without greatly changing mass loss. The direction of the solar magnetic field near the object rotates with the sun roughly every 27 days and flips across sector boundaries, regions where the field polarity changes sign. Crossing a sector boundary can rearrange the draping pattern and tail shape quickly. Observationally, that can look like a kink in the ion tail, or a sudden swing in polarization angle. If the body is active in short-lived bursts, each burst seeds a packet of ions that are then sorted and stretched by whatever field geometry prevails that day, creating a time-stamped ladder of filaments downstream. By comparing images taken days apart, you can sometimes pick out these time slices moving away, a slow-motion record of both the object's breathing and the wind's changing mood. Inside and just above the surface, magnetic effects are indirect but still important. Electrical currents can't flow far through insulating dust and ice, but they can flow along plasma paths in the near-surface gas, creating tiny return currents that help close the circuit with the solar wind. Where narrow jets punch out, the plasma density can be higher, so these jets become preferred channels not only for mass, but for charge and current. That in turn modifies the local electric field, which feeds back on how easily grains lift and on how ions accelerate as they depart. The overall picture is a loop. Sunlight heats and liberates gas. Gas and dust alter local plasma. Plasma interacts with the magnetic field. The field shapes the escaping flow. The shaped flow changes how and where the next round of dust and gas leaves. If the object is tumbling, the magnetic conversation acquires a rhythm. A jet that rotates in and out of sunlight modulates the pickup ion source, turning the wave power up and down at the spin frequency. A spin axis that points differently as the object travels shifts which latitudes on the surface see the wind head on. Over days, the signatures in polarization maps or narrowband images can drift in phase, mapping not only the field but the spin geometry. In the ideal case, dense, multi-night datasets, analysts can invert these drifting patterns to estimate the orientation of the spin pole and the timing of jets, cross-checking results from purely photometric light curves with magnetic and plasma tracers. A natural question is whether any of this produces true radio noise that we could hear if translated to audio. The answer is that plasma waves and stimulated emissions do create narrowband and broadband features that instruments convert to voltages and then to spectra. Spacecraft near comets have recorded rising and falling tones near the local plasma frequency, bursts at ion cyclotron harmonics, and hiss-like continua when turbulence is strong. From Earth, we usually don't detect those plasma waves directly because the signals are faint and absorbed or masked. Instead, we measure molecular lines and polarization and infer the plasma environment indirectly. But the physics is continuous. The same outflow and draping that would sing to a passing probe also leave fingerprints that telescopes can read across the electromagnetic spectrum. Finally, magnetic context helps avoid overclaiming surprises. A sudden kink, a bright knot, a sideways fan, these can look like rule breaking if you only expect gravity and sunlight. When you fold in the magnetic field and the plasma it carries, the features become expected variations. Draping lines, steer ions, sector crossings, flip tail geometry, pickup ions, pump waves, charged grains, tilt polarization, and subtle electric fields help decide which dust escapes. The whispers are always there, low and soft, shaping the space around a small world so gently that only careful, repeated measurements reveal the pattern. And once you learn to listen, the pattern explains why the environment seems too orderly to be noise and too messy to be music at the very same time. When tiny grains drift away from a small body, they carry a record of where they formed and what they endured. A grain's structure, composition, and surface scars are like dates stamped into metal. They don't tell the whole story, but they fix key moments in time: condensation in a hot nebula, slow alteration in cold darkness, jolts from micrometeoroid impacts, and long exposure to cosmic rays. Even when we cannot collect those grains directly, their memory shows up in the way they scatter and emit light. Under infrared spectrometers, silicate dust reveals broad features near 10 and 20 micrometers that tell us whether the material is mostly amorphous, glass-like and disordered, or crystalline, with atoms locked into neat lattices like olivine and pyroxene. Amorphous silicates point to rapid cooling or radiation damage. Crystalline features hint at heating above the glass transition, followed by slow cooling. Seeing both together means the dust population is a blend of histories, some grains forged in fire and others preserved in ice-cold archives. Size matters because it changes how a grain interacts with light and forces. Submicron grains scatter sunlight almost like molecules, with strong wavelength dependence that makes colours tilt. Micron-scale grains forward scatter, enhancing brightness when we look near the sun's direction. Millimeter grains contribute more to thermal emission than to sharp optical features. Observers turn these tendencies into diagnostics, If the coma brightens more than expected at large phase angles, forward-scattering small grains are abundant. If polarization grows steeply with angle, fluffy aggregates, grains made of many tiny monomers stuck together, are likely. Those aggregates behave like cosmic snowflakes, extremely porous, low density and fragile. Their porosity increases the ratio of area to mass, which strengthens radiation pressure and changes how the dust tail unfurls. The grain size distribution, how many of each size, often follows a power law. Changing the slope of that law subtly reshapes the tail and the colour of the coma, letting us infer whether the source favours fine powder from brittle crusts or larger clumps flaking off from cohesive patches. Radiation pressure sorts grains by size once they leave the nucleus. The strength of the push is commonly summarised by beta, the ratio of radiation pressure forced to solar gravity. Beta is close to 0 for big, heavy pebbles, and approaches 1 for the tiniest grains. As a result, the dust population fans into families of curved trajectories. Map those families and you're effectively reading a diary of release times and sizes. In deep images, this sorting shows up as narrow striae and gentle rays. In time series, features launched on different days peel away and mark the calendar downstream. By overlaying Sindine synchrone models, curves of constant size and constant release time, on images, analysts can back out when bursts occurred and which sizes dominated. Cross-checking with photometric spikes and jet inferences from the light curve. Temperature writes another line into the memory. As grains absorb sunlight and re-emit heat, their thermal spectra betray composition and texture. Compact glassy silicates radiate differently than fluffy aggregates with voids. If a grain carries organic mantles, carbon-rich coatings built by chemistry in cold, irradiated environments, its mid-infrared features flatten and its albedo drops, making the coma redder in reflected light. Observations through water bands near 3 micrometers can reveal whether icy coatings survive on the smallest grains. Far from the sun, such coatings can persist for minutes to hours, softening scattering properties and adding faint absorption features. Nearer in, they sublimate quickly, leaving dehydrated cores that then darken and heat more efficiently. That sequence, icy to bare, plays out across distance, so following colour and thermal changes along the tail lets us watch the transformation unfold. Cosmic rays and ultraviolet sunlight leave microscopic damage trails that accumulate over eons, broken bonds, amorphized rims, and nanophase metallic iron embedded in silicates. These modifications tilt optical properties towards space-weathered, darker, redder, and less reflective at short wavelengths. Interstellar travellers may have unusually thick weathered rims due to their long residence in very cold, low-density space, where chemical healing is rare. If their dust looks darker and more reddened than typical fresh cometary dust at the same phase angle, that is one clue. If polarization curves are shifted relative to solar system averages, that is another. Laboratory analogues, irradiated glasses and organics made in vacuum chambers, provide templates to interpret those shifts, turning subtle photometric trends into statements about exposure history and the balance between radiation damage and thermal annealing. Isotopes, in principle, are the oldest memories, written when atoms were built in stars and supernovae, and then mixed into protoplanetary disks. We cannot weigh isotopes remotely with the same precision as a mass spectrometer, but some coarse indicators leak into spectra. Deuterium to hydrogen ratios influence the strengths of certain vibrational features in ices. Carbon and nitrogen isotopes slightly shift band centers in nitriles and cyanides. In situ missions have measured exotic grains with isotopic ratios that scream pre-solar, older than our solar system. For a passing visitor, we rely on comparison. If gas phase ratios inferred from spectra fall outside the common solar system comet ranges, that flags a different chemical kitchen. If they sit comfortably inside, it does not erase the interstellar label, but it says the chemistry of disks may be more universal than our sample size suggests. Either outcome teaches us something valuable about how widespread particular chemical pathways are. Grain mechanics, how easily grains stick, break and loft, preserve notes about the surface they left. Cohesive surfaces release larger chunks, brittle, dehydrated crusts shed fine powders, sintered icy layers produce compact pellets that survive farther before crumbling. These tendencies ripple through observable quantities. Large chunks make shallow photometric phase curves and strong thermal emission, with weak polarization. Fine, fluffy dust pushes polarization higher and enhances forward scattering. If repeated, short-lived outbursts inject swarms of very fine grains. The coma brightens sharply, then fades as the grains are pushed away. A slow, steady release of larger grains creates a persistent, low-contrast halo and a broad, muted tail. Matching these behaviors night by night builds a consistent portrait of near-surface strength, porosity, and layering without ever seeing the surface directly. Magnetic and electrical environments modify dust after launch, and those modifications also encode conditions. Charging by sunlight and the solar wind can align elongated grains very weakly with the local magnetic field, nudging polarization angles in systematic ways. Tiny grains that charge strongly can be filtered out of certain regions, leaving shadows in the distribution that depend on field orientation and plasma density. If a sector boundary passes the large-scale flip in solar magnetic polarity, the ion tail can kink and the dust polarization map can twist. Catching such changes and tying them to known solar wind conditions lets us separate memory written at launch from memory written in flight, keeping the origin story and the journey story in their proper chapters. Near the nucleus, dynamics can trap or recycle dust. Millimeter-scale grains that fail to reach escape speed can hover briefly in slow arcs and then drift back down, smoothing slopes and filling pits. Over many rotations, that fallback builds mantles that are darker and finer than raw subsurface ice-rich material. When a new crack opens, jets can excavate through that processed layer and fling out older, brighter grains. Photometrically, this alternates the dust colour and albedo of the coma on timescales of days to weeks. Darker periods dominated by reprocessed surface grains, brighter periods seeded by deeper, fresher material. Tracking such colour cycles and correlating them with any measured changes in non-gravitational acceleration offers a cross-check. Deeper excavation should accompany stronger, more directed thrusts, and a modest bluid colour shift if cleaner ice-rich grains are present. The tail itself is a stratified archive stretched over millions of kilometres. Close in you see today's and yesterday's grains. Farther out you intercept last week's and last month's, each cohort aging, ice is gone, organics browned, structures compacted by micro-collisions. Long, deep exposures can pull out multiple faint parallel filaments, the record of pulses in release rate, one filament per episode. By measuring their spacing and curvature, you can solve back to the emission times and the prevailing beta values, effectively reading a barcode of activity. If the spacing tightens near the time of closest approach to the Sun, it reflects increased jetting frequency or stronger sorting. If it loosens, activity likely smoothed into a steady flow. Spectropolarimetry combines two powerful tools, spectra and polarization, to fingerprint grains more uniquely. Polarization often peaks at wavelengths where scattering efficiency is highest for the dominant grain size, so a wavelength-dependent polarization curve can reveal a preferred size, even when broadband colours look ambiguous. Superimposed narrow emission lines from gas must be accounted for. Doing so cleanly leaves the continuum polarization due to dust alone. Comparing that continuum across wavelength and phase angle to libraries built from solar system comets tells us whether the grains are unusually compact, unusually fluffy, unusually carbon-coated, or within the familiar range. An outlier curve isn't an anomaly to hype. It's a specific pointer to microphysics, monomer size in aggregates, degree of compaction, or mantle fraction that we can test in lab analogues. Ultimately, dust that remembers helps connect scales. A nucleus meters across sheds grains, microns across that record conditions from astronomical units to interstellar light years. The same grains control how sunlight pushes the nucleus through jet feedback, how bright the coma becomes, how much thrust and non-gravitational forces deliver, and how the object's environment couples to the solar wind. Each measurement, an infrared bump, a polarization angle, a forward scattering surge, a faint filament in the tail, reads a small part of the archive. Read enough parts, cross-check them, and the scattered memories assemble into a coherent history. What the material was before it arrived, what the surface is like now, and how the journey through our neighbourhood is adding one more layer to the story the grains will carry as they keep drifting outward. As an object falls inward toward the sun, sunlight does more than make it brighter in our telescopes. It raises the energy budget everywhere, on the surface, just beneath the surface, and throughout any dust cloud wrapped around it. The amount of sunlight increases sharply with a decreasing distance, following a simple inverse square law, so even a modest inward step delivers a noticeable jump in heating. If ices are present, their sublimation rates climb non-linearly with temperature. A few degrees can turn a trickle into a flow. This is why many comets flare before and around their closest approach to the sun. But not every object answers with fireworks. Sometimes the expected surge softens into a plateau because other processes, like crust growth, shadowing, and gas flow through narrow cracks, act like valves that limit how much mass can get out at once. The uppermost layer controls the conversation with sunlight. If that layer is porous and fresh, heat sinks in easily and reaches ices tucked just below, turning them to gas that can escape freely. If the layer has been processed, baked, sintered, and darkened by earlier visits or long exposure, the pores can close and grains can fuse, building a mantle that insulates the interior. Gas rising through such a mantle loses heat and pressure. Some of it recondenses as frost deeper down, some reaches the surface only in specific weak zones or where cracks remain open. The result is a handful of stable vents instead of a broad uniform exhale. In observations, that difference is the gap between a dramatic global brightening and a gentler, controlled rise that seems to level off despite the increasing sunlight. Not all ices respond at the same distances. Far from the sun, key highly volatile species like CO and CO2 can sublimate. Nearer in, water becomes the main driver. If CO or CO2 dominates early activity, the object can look lively at large distances and then seem to stall temporarily as those reservoirs deplete or migrate, only to recover as water ice warms enough to take over. That handoff can create a two-step activity curve, an early bump, a quiet shoulder, and a later rise. If the water supply is shielded under a tough crust, even the later rise may stay subdued. Observers sometimes summarize this behavior with a simple rule Q, proportional to R to the power of -n, where Q is gas production and R is distance from the sun. The exponent Nn can be small, a slow climb, or large, a sharp surge, and it often changes across regimes as different volatiles and surface states take turns setting the pace. Geometry adds another lever. Where sunlight lands most directly depends on the spin axis. If the pole points such that one hemisphere leans into the sun near perihelion, that summer hemisphere can host the main vents and receive steady heating. If the pole lies sideways, the subsolar point sweeps across many longitudes and latitudes each rotation, sharing heat more evenly. These seasonal and diurnal patterns shape how cracks open and where frost can persist between sunrises. A vent near the noon belt feeds steadily and steadily sculpts its own collar of fallback dust. A vent nearer the terminator wakes and sleeps every spin, pulsing gas and dust on a schedule that rides atop the overall trend set by distance to the sun. In light curves, the steady case smooths brightness, the pulsed case imprints a repeated ripple whose contrast changes with distance. The coma responds as a coupled system of gas, dust, and radiation. Gas speeds typically sit in the hundreds of meters per second near the source. The smallest dust grains hitchhike on that flow, while larger grains lift more reluctantly and can fall back if gas is scarce. As sunlight grows stronger, more fine dust is lofted, and radiation pressure sorts it by size, sharpening forward scattering effects at certain viewing angles. That can make the object appear to brighten faster than a bare rock would, even if the nucleus activity is merely steady. At the same time, increasing dust can partially veil the nucleus and wash out rotation signatures in the visible light curve, so observers counter by using tighter photometric apertures or by switching to gas-sensitive filters that track species like OH or CN to find out whether gas production is actually rising or if dust is doing most of the talking. Thermal inertia, how quickly a surface warms and cools, decides whether activity peaks before, near, or after perihelion. A low inertia, powdery surface heats quickly and can reach maximum gas flow slightly before the actual closest approach, then fade just as quickly afterward. A higher inertia surface, or one blanketed by a crust that stores and slowly releases heat, can lag. Energy absorbed near perihelion continues to drive sublimation after the turning point, shifting the peak to later dates. This pre-post asymmetry is common in comets, and it can be magnified if dust redeposits unevenly after perihelion, closing vents on one flank while opening others where stresses crack the warming crust. In simple plots, one side of the curve climbs steeper or sits higher than the other. In images, jet fans migrate in latitude as the subsolar point slides with the changing geometry. Small bodies pay a price for stronger activity, torque. Gas jets pushing off centre act as tiny thrusters that can spin the nucleus up or down. Near perihelion, when jets are strongest, the spin period can drift measurably, and the pole direction can wander. If spin-up crosses structural limits, landslides or even partial shedding can occur, feeding a short-lived outburst of dust that looks dramatic against a generally smooth plateau. Whether that happens depends on size, shape, internal cohesion, and where the jets emerge. Many objects pass perihelion without incident because their vents are weak or well placed and their interiors are strong enough. Others show brief hiccups, narrow spikes in brightness and dust production that subside within hours to days as geometry and stresses rebalance. Closer to the sun, infrared emission becomes a powerful complementary gauge. Visible light mixes reflected sunlight from dust and surface with any glow from the gas. Thermal infrared isolates the heat re-radiated by the dust and, if the nucleus is large enough, by the warm surface itself. Comparing visible and infrared light curves helps separate area, how much stuff is present, from temperature, how warm it is. A flat visible curve but rising infrared can indicate heating without much extra dust. A rising visible curve with modest infrared growth can indicate more fine dust with low thermal inertia. A rise in both usually marks true activity growth. Wavelength-dependent polarization adds detail. It often peaks at phase angles that are sensitive to grain size and texture. So changes in polarization while closing on perihelion can reveal whether the dust population is shifting toward finer or coarser grains as venting strengthens. The solar wind and magnetic field also grow more intense nearer the sun, and their influence shows up most obviously in ion tails and in the draping of field lines around the coma. If a solar storm arrives, an enhanced flow, or a coronal mass ejection, the ion tail can kink or brighten quickly, sometimes within hours, even if the nucleus output doesn't change. Coordinating such space weather events with the object's timeline keeps interpretations honest. A sudden tail change at small elongation may be the sun's breath, not the nucleus's. Meanwhile, higher ionization rates near the sun convert a larger fraction of the escaping neutrals into ions, which feeds stronger pickup ion waves and can enhance radio emission in certain molecular lines, offering another set of diagnostics when direct imaging is hard. Observationally, the approach to perihelion often brings practical limits. The angular separation from the sun shrinks, atmospheric scattering brightens the daytime sky, and safe pointing constraints for large telescopes and spacecraft reduce coverage during exactly the most interesting days. Teams plan around that solar gap by bracketing the closest approach. Dense nightly photometry and spectroscopy on the way in, then again as soon as elongation recovers. For the missing window, models step in, constrained by what came before and what follows after. If activity was climbing with a certain exponent pre-perihelion, and the surface properties look unchanged, post-perihelion, a smooth interpolation is reasonable. If the post-perihelion state is clearly different, new colours, new polarisation, altered spin, then something changed at or near closest approach, and the plateau or step in brightness carries more weight. Dust mantles evolve rapidly under the solar caress. Finer grains, once lofted, either escape or fall back. Fallback preferentially darkens and insulates, making subsequent heating less effective in that patch. At the same time, areas kept clean by persistent jetting can brighten because fresher, more reflective material remains exposed. This patchwork creates a surface that co-evolves with the light curve. Subtle colour mosaics and changes in amplitude track which sectors are active. Over days to weeks, vents can migrate a few degrees as cracks open and close. Over a single rotation, self-shadowing by cliffs and ridges modulates the heartbeat of jet strength, a pattern that rides atop the smoother trend set by distance to the sun. In tail morphology, increasing sunlight sharpens the size sorting and stretches the dust into broader fans. Forward scattering near certain geometries boosts apparent brightness dramatically, sometimes enough to mimic an outburst if phase angle corrections are not applied. Analysts therefore anchor photometry to standard phase functions and run Sindine synchrone maps to make sure that a bright limb or a new ray is a true mass loss change rather than a viewing angle effect. When strong forward scattering is present, it becomes an ally. The enhanced glow at large phase angles makes it possible to trace the finest grains, providing sensitive probes of the smallest size bins and of recent release times during the perihelion passage. Energetically, the inner few tenths of an astronomical unit are where water ice sublimation, thermal irradiation, radiation pressure, and ionization all peak in tandem. The nucleus tries to regulate. As more energy arrives, more goes into latent heat of sublimation and into lifting dust, which cools the surface by carrying energy away. As mantles thicken, less energy reaches the ice and more is irradiated as heat. That self-regulation is why a smooth plateau is not only possible but common. The system finds a balance between input and output, set by porosity, vent geometry, and grain sizes. A true runaway requires either fresh, widespread exposure of ice or large structural changes. Absent those triggers, the quiet lean into sunlight is a sign of stability, not a failure to respond. For interstellar visitors, the same rules apply with an extra twist. Their surfaces may have been processed for ages by deep space radiation, creating thick, coherent crusts that resist easy venting until strong heating arrives. If those crusts endure, the perihelion passage can look textbook calm even under high solar input. If they crumble locally, the response can be sharp but localized, producing brief, narrow peaks without changing the overall trend. In either case, the comparison between pre- and post-perihelion states, spin rate, pole orientation, color, polarization, and the strength of any non-gravitational acceleration reveals whether the solar crest merely warmed the skin or reached deeper and rearranged the plumbing. Seen that way, a gentle brightening followed by a plateau is not a disappointment. It is a fingerprint of how heat, ice, dust, and geometry agreed to share the sun's energy on this particular pass. Turning a stream of faint measurements into a physical picture is an inverse problem. We see effects, brightness, spectra, positions, and ask what causes, shapes, spin, jets, composition could have produced them. Inverse problems are often ill-posed. Many different causes can explain the same effects within the error bars, so modelling becomes a disciplined way to rule out what's inconsistent, rank what's plausible, and quantify what we still cannot tell. The workflow starts simple. Subtract the predictable pieces, distance changes, phase, angle trends, planetary tugs, examine the leftovers, and then add the smallest number of extra assumptions needed to make the model and the data agree. If a model needs too many knobs to fit small features that could be noise, it's probably overfitting. If it can't reproduce the big features even with reasonable knobs, it's probably missing core physics. There are 3 broad model families that get woven together. The first describes the solid body: shape, spin state, surface reflectance, thermal inertia, and interior layering. For shape and spin, light curve inversion takes time series of brightness and solves for a convex 3D model and a rotation pole that reproduce the observed periodicity. When geometry changes enough during the apparition, the solution becomes stable, but ambiguities mirror poles. Stretched long axes remain unless anchored by an occultation chord or thermal size. Thermophysical models add heat conduction into the upper centimeters, shadowing by local relief and re-radiation. By matching visible and infrared light curves together, they constrain size, albedo, and thermal inertia. Reflectance is handled with empirical phase functions or with more physical scattering laws, e.g. Hapke. But those introduce parameters for roughness and single-particle phase functions that correlate with shape, hence the need for multi-wavelength data to keep parameters from drifting into non-physical corners. The second family models the gas and dust environment, what ices sublimate at what rates, how gas expands and accelerates dust, and how radiation pressure and the solar wind reshape the flow. Simple Hazer modelers treat the coma as a spherically symmetric outflow with parent and daughter species, letting spectra turn into gas production rates. When symmetry is clearly broken, fans, jets, corkscrews, direct simulation Monte Carlo, DSMC, or fluid approximations map gas, leaving specified vents on a rotating body, including shadowing and seasonal illumination. Dust dynamics then sits on top, grain size distributions, radiation pressure parameter beta, and Syndine synchrone maps that convert when and how big into where features should be found in images. Polarization and color trends restrict grain porosity and monomer size in aggregates, keeping the dust model honest when many combinations could match the same broadband brightness. The third family handles trajectory physics and small forces. Orbit fits begin with n-body gravity, and then add non-gravitational accelerations parameterized along radial, transverse, and normal axes. If the residuals shrink and the parameters follow sensible distance dependencies, E/g 1 over EL squared for radiation pressure, water sublimation laws for jets, the added physics earns its keep. When gas production and light curve evidence suggest changing spin or migrating vents, those time dependencies are folded into the acceleration law as well. Propagating orbit clones, an ensemble of fits sampled from the covariance matrix, tests whether predictions are robust or delicately tuned to a few data points. All of this runs inside a statistical wrapper. Least squares gives a best fit, and uncertainties when their errors are Gaussian and independent. Robust loss functions, Huber, Cauchy, soften the impact of outliers like a cloudy exposure or a blended star. Bayesian inference formalizes prior knowledge. Spin periods for objects this size are usually between x and y. Thermal inertia is non-negative and rarely exceeds z, and yields full posterior distributions for parameters via Markov chain Monte Carlo, or nested sampling. Priors prevent wandering into impossible regions, posteriors reveal degeneracies, for instance how a slightly larger body with lower albedo can mimic the flux of a smaller, shinier one. Model comparison uses information criteria, AIC, BIC, or evidences. If adding a jet improves the fit only trivially while introducing 4 new parameters, the simpler jet-free model wins by Occam's razor. Because data are sparse and varied, cross-validation is essential. Posterior predictive checks ask, do synthetic data drawn from the fitted model look like the real data we didn't use in the fit? Different nights, different filters, different apertures. If not, the model captures quirks rather than physics. Hierarchical models go one level up. Instead of treating every night's calibration or every telescope's 0 point as fixed, They fit those as nuisance parameters with priors, so their uncertainties flow into the final physical uncertainties rather than being silently ignored. Non-detections, images where the object is too faint, are folded in as censored data, which keeps the model from inventing activity when observations explicitly fail to see it. Heat flow and vent physics are notoriously degenerate, so modelers use Occam grids. Start with a 1D conduction layer, a single vent as, and a fixed spin, only introduce multiple layers, varying porosity, or migrating vents if the residuals demand them. Regularization, Tikhonov sparsity, tempers solutions that try to put a separate vent under every wiggle in the light curve. Synthetic truth exercises generate fake observations from a known answer, then see whether the pipeline recovers that answer, catch biases before real data are interpreted. When pipelines disagree across groups, code and input data are swapped in round-robin tests to separate algorithmic choices from calibration differences. Uncertainty propagation is as important as the central values. Covariance between size and albedo, between pole and shape elongation, and between gas production and dust contamination can fool a confident plot if not tracked end to end. Sensitivity analyses vary at one assumption at a time, e.g. the adopted phase law or grain porosity, to reveal which conclusions are brittle and which are stable. Reporting should reflect that. A narrow error bar that ignores systematics is less honest than a broad one that includes them. Reproducibility matters too. Listing the version of star catalogues, reduction software, and solar wind ephemerides used allows others to rebuild the result and test new assumptions cleanly. Population thinking helps even for a single object. Prior knowledge from 1I/Oumuamua style behavior and 2I/Borisov style behavior becomes soft priors, not rules, but expectations. If 3I Atlas looks between priors broaden. If it lands clearly in one camp, priors tighten. Selection effects, what we tend to discover and when, also get modelled. Surveys are biased toward objects that brighten at large phase angles helped by forward scattering, or that enter the sky where cadence is high. Accounting for those biases stops us from concluding that plateaus are common, or spin periods cluster near X, when we have simply been more likely to notice those cases. Real-time modelling during an apparition is iterative. Early, with a short data arc, models are deliberately conservative. Wide posteriors, few parameters, many clones. As more nights arrive, period aliases fall away. The pole solution firms up and jet parameters can be promoted from fixed to fitted. Observing plans feed on the model's forecasts. Occultation predictions, best geometries for polarization. Phase angles that maximize forward scattering to probe small grains, and the new data in turn tighten the model. When the target dips too near the sun to observe, ensembles carry the fit through the gap. After reacquisition, divergences between predicted and measured states flag either unmodelled physics during the gap, a brief outburst, a spin change, or overconfidence earlier. Computational details matter more than their glamour suggests. DSMC and thermophysical models can be expensive, so modelers use surrogates. Pre-computed libraries of solutions, emulators, that interpolate rapidly inside the Bayesian loops. Parallel tempering keeps MCMC chains from sticking on narrow ridges of parameter space. Reparameterizations, fitting log of positive quantities, using angles in sine-cosine pairs, improve convergence. Unit tests on subroutines, version-controlled repositories, and archive configuration files defend against silent regressions when the code changes mid-campaign. Transparent data releases, photometry, spectra, astrometry, and the masks and apertures used. Let independent teams try alternative priors or physics and see whether conclusions are truly robust. Even when a model fails, it teaches. If every physically reasonable vent pattern still predicts colour changes that aren't seen, the conclusion is not mystery solved, but jets aren't the driver and attention shifts to radiation pressure or thermal re-radiation. If a convincing radiation pressure fit implies an area-to-mass ratio that would demand an impossible density for the observed thermal flux, that contradiction forces a rethink of shape, porosity, or albedo assumptions. Contradictions are progress markers. They show exactly where the current map ends and where the next measurement should point. In the end, models in the dark are not guesses. They are structured arguments that survive attempts to break them. They balance simplicity with sufficiency, make predictions that new data can test, and keep uncertainties visible so that stories do not outrun evidence. For a faint fast visitor like 3i Atlas, that discipline is the difference between a tidy tale that fits our hopes and a reliable picture that fits the sky. When we talk about interstellar visitors, two clear reference points help frame expectations. The first is the one that surprised everyone by behaving unlike a typical comet, an elongated, faint object with no obvious dust coma, a changing light curve consistent with a complex spin, and a small but measurable non-gravitational acceleration that could be explained either by very low-level outgassing or by radiation pressure acting on a body with a relatively high area-to-mass ratio. His colours looked broadly comet-like, slightly red as you would expect for the material processed by radiation, but spectra showed no strong gas lines. The second reference point arrived looking and acting like a classic comet. It displayed a persistent dust coma and tail, clear gas emissions in standard filters, and non-gravitational forces fully consistent with ordinary jets from sublimating ices. Put simply, the first taught us that not all interstellar objects announce themselves with a misty halo, and the second reassured us that at least some do. Those two cases outline a spectrum that is useful for thinking about any new arrival. On one end you have low activity, perhaps because a tough crust limits venting, or because supervolatile ices are scarce near the surface. In that regime, brightness is dominated by the bare nucleus, and small changes in its presented area and surface scattering as it rotates. The lack of an obvious coma makes size, shape, and spin estimates very sensitive to assumptions about reflectivity and phase behaviour, and any small trajectory drift becomes a focus of debate because gas is hard to confirm. On the other end you have vigorous activity where gas species like CN and OH and dust continuum are straightforward to measure. In that regime, classical coma models transform spectra into production rates. Dust diagnostics like AFRO behave as they do for familiar comets, and non-gravitational forces follow the same distance-dependent laws we use in the solar system. Most of the heavy lifting is then in mapping vents to the rotation state rather than improving that activity exists. Light curves are central in both cases but play different roles. For a minimally active object, the light curve is the primary shape and spin probe. Amplitude speaks to elongation, multi-period behaviour points to tumbling, and phase angle dependence reveals surface texture and opposition effects. For an active comet, the nucleus signal rides on top of a dust pedestal. Careful aperture choices and coma subtraction are needed to recover the rotation signature, while the larger aperture photometry tracks dust output. Comparing these two styles taught observers to alternate apertures and filters quickly, so that a single night yields both nucleus-sensitive and coma-sensitive measurements. That habit carries straight into the study of any third object. Composition is where the contrast becomes vivid. In the comet-like case, emission bands from common radicals CN, C2, C3, and daughter products of water show up as a familiar comb in spectra, and sometimes CO or CO2 can be inferred from infrared features or from activity at large distances where water would be sluggish. In the low activity case, reflectance spectra are mostly smooth, with only broad colour trends hinting at organics or space-weathered silicates, and gas upper limits become as important as detections. We didn't see X down to Y is a strong statement that shapes the space of plausible activity models. Taking those lessons forward means planning for both outcomes. Have narrowband gas filters and IR capability ready if a coma appears, but also have high-precision broadband photometry strategies ready if the object stays bare. Non-gravitational dynamics is the shared bridge between the two archetypes. In the active case, the extra acceleration aligns with expectations from venting. It scales with the solar energy input, points in directions you can reproduce with vents at certain latitudes on a rotating body, and rises and falls with measured gas production. In the bare-looking case, the same-sized acceleration demands other explanations if gas remains unseen. Radiation pressure becomes plausible if the body is unusually thin or porous, increasing area per unit mass. Thermal re-radiation, Yarkovsky-like forces, becomes plausible if the surface has the right thermal inertia and spin geometry. The important methodological lesson is to couple orbit fitting to physical diagnostics. Check whether the magnitude and direction of the required force makes sense, given the light curve, colours, and any spectral constraints, rather than treating trajectory and physics as separate puzzles. Population thinking matured because of these two. Before the first detection, models of ejected planetesimals from forming planetary systems suggested that interstellar debris should be common, but we had no direct detections to set the normalization. The odd Cumulus case briefly raised the possibility that we preferentially detect high area-to-mass objects, because they brighten more at certain geometries or because they wander into survey sweet spots, while the comet-like discovery reminded us that normal icy fragments are indeed detectable with current surveys. Together they improved estimates of how many objects per year pass within the reach of wide-field systems, and they pushed survey pipelines to flag slow, faint movers more aggressively, even when they don't look like textbook comets. Survey cadence and geometry also entered the conversation. The elongated low-activity object was visible for a short window, and at modest phase angles, so a lot of its mysteries trace back to the limited viewing geometry and time on target. The active comet lingered longer, could be followed pre- and post-perihelion, and offered better phase angle diversity, which reduced degeneracies in spin and dust modelling. That contrast led to a practical rule for future visitors: front-load observations when discovery happens late in an apparition, and diversify techniques, photometry, spectroscopy, polarimetry, thermal IAR, when discovery comes early and time allows a full campaign. It also focused attention on the value of southern and northern facilities working in relay to beat 24-hour aliases in light curves and to maintain coverage through weather gaps. Dust taught complementary lessons. In the active comet, dust size distributions and polarization curves look much like solar system comets, a mix of porous aggregates and compact grains, forward scattering behavior at large phase angles, and AFRHO trends that scaled in familiar ways with heliocentric distance. In the bare-looking case, any dust must have been either extremely low in quantity or confined to sizes and textures that didn't produce strong signatures at the observed angles and wavelengths, that forced dust models to consider extreme porosities, unusual monomer sizes, or rapid grain destruction close to the source. Carrying both possibilities forward encourages observers to acquire polarization and color data even when a coma seems absent. Non-detections constrain microphysics and keep exotic interpretations honest. Spin states framed by the pair are also instructive. The low-activity object likely tumbled, with multi-period light curves that slipped in phase over days, suggesting a history of torques and perhaps a stiff interior that hadn't yet damped into principal axis rotation. The active comet showed behaviour consistent with a more stable spin, and any period changes could be linked to jet torques near perihelion. That contrast underscores the need to search for P.P period drift. In all cases, in an active body, P.P maps jet torque. In a quiet body, P.P limits thermal or radiation torques and constrains shape and density indirectly. Either way, repeated, well-calibrated light curves over weeks pay off. Even the broader kinematic context matters. Interstellar objects arrive with velocities set by their home systems and by galactic dynamics. Some will move close to the local standard of rest, others will carry significant peculiar velocities. The first two showed that we should expect a range. Arrival directions and speeds won't all point to one source or one ejection mechanism. That diversity cautions against over-interpreting a single object's path as evidence for a particular kind of planetary system. Instead, it argues for building a small catalogue with well-measured kinematics, so we can look for clustering that would hint at common origins. For planning and interpretation, the pair established a decision tree. If a new object shows gas early, deploy narrowband filters, measure production rates, model jets on a rotating body, and tie non-gravitational forces to those rates. If it does not, prioritize dense light curves across multiple filters and phase angles, pursue deep spectra for weak gas limits, and assess whether radiation pressure or thermal thrust can explain any trajectory drift without violating thermal and photometric constraints. In both branches, collect polarization if possible, and coordinate infrared to break albedo-sized degeneracies. That tree keeps campaigns efficient and keeps claims anchored to measurable quantities. Finally, they refined our sense of surprise. The first object reminded us that absence of a coma is not absence of physics. Subtle forces can matter, and small bodies can carry shapes and surfaces that break our solar system intuitions without breaking physical laws. The second reminded us that interstellar space can deliver perfectly ordinary comets, letting us apply familiar tools to unfamiliar origins. With those bookends in mind, any third object is less of a mystery and more of a test. Does it sit near one end? Does it land in the middle? Or does it trace a new path through parameter space we haven't sampled? Each outcome is informative. A middle case tightens the continuum between extremes. An extreme case strengthens one tail of the distribution. An outlier forces new modelling and lab work. That is why comparisons are not just historical notes, but working instruments. They set the axes, mark the corners, and give us a calibrated grid on which to place the next point. The places where discoveries are made rarely feel like movie scenes. They are rooms with low light to keep eyes dark adapted, screens showing plots and images, quiet voices trading short sentences, and a steady rhythm of checking, logging, and deciding. The debates are not loud. They're careful. Someone points at a residual plot and says, "This bump is phase angle," and someone else says, "or catalogue bias," and both notes go into a list. The list matters because it becomes the plan. Re-reduce last night's frames with a different star catalogue, try a tighter photometric aperture to cut coma contamination, and rerun the orbit fit with the suspect observations down-weighted. The culture is to distrust the first, easiest explanation without dismissing it, and to keep a running notebook of every assumption and every change, so that in a week, when the picture is clearer, no one has to rely on memory to reconstruct why a number moved. Most of the work is data hygiene. Raw images come in with bias, dark current, and flat-filled structure. Pipelines subtract and divide and align, but humans still look at the stamps because pipelines miss things. Faint clouds, a trailed background star blending with the target, a hot pixel under the centroid. Astrometry is tied to a reference frame, often Gaia, but one observer's clean catalogue subset is another's overzealous filter that threw out useful stars near the galactic plane. Photometry needs stable comparison stars. Someone checks for variables in the ensemble, notes colour terms between instrument and standard system, and records sky brightness and seeing, so that later, if an amplitude changes, the team can tell whether the sky changed or the object did. This attention to unglamorous details is not bureaucracy. It is the difference between a real 0.03 mag effect and a ghost from the reduction. Disagreements are handled with experiments rather than opinions. If one person thinks non-gravitational acceleration is present and another thinks it is a calibration artifact, they design a blind test, share a curated subset of positions without telling which nights were cloudy and which were clear, run independent fits, and compare. If both fits pull in the same direction, the case strengthens. If they diverge, they trace the difference to choices, a set of outlier rejections, a different weighting scheme, a missing light time correction. The winner is not the loudest voice, but the method that survives changes in assumptions. When tempers rise, the room returns to shared goals. Forecast the position for tonight, choose filters to maximize information, and document everything so that the next person on shift can reproduce the result. Because telescope time is scarce, teams triage. A whiteboard or shared channel lists high-value observations. phase angles near opposition to nail the phase function, a long continuous run to break period aliases, a narrow band night to measure gas when the moon is down, a thermal IR slot to constrain size when the object is still bright enough. If two facilities can see the target, they split roles. One does fast cadence in a single filter for light curves, the other does multicolour snapshots for colour trends. Coordination avoids duplication and fills gaps, and it requires trust. A small observatory's dozen precise points can be as valuable as a big telescope's spectrum if they land exactly where the model is weak. The language in these rooms is precise on purpose. People say consistent with rather than proves, upper limit rather than nothing there, marginal rather than exciting hint, because they know how fragile early patterns can be. Error bars are argued over like budgets. Are they internal, photon noise only, or do they include systematics, flat field structure, colour terms, scintillation? Are they independent from point to point or correlated within a night? Conservative errors widen the band of plausible models, but they keep claims honest and reduce later retractions. Plots carry residuals because a fit without residuals hides as much as it shows. Tables include observing geometry and calibration stars so that someone else somewhere else can run the same math and see if they land in the same place. Null results have status. A night that sets a stronger limit on gas lines or polarization is logged with care because limits carve away parameter space just as detections do. When rumours circulate, we heard of groups or CN, the response is not panic or hype but a checklist. Match dates and geometry, see whether our sensitivity would have caught the same thing, adjust plans if needed to test the claim independently. Preprints enable fast sharing, but the internal rule is to read methods first, conclusion second. If a claim leans on a model, someone tries to rerun the model with the posted code or a reimplementation. If the code is not posted, they approximate it, note the gaps, and ask for details without assuming bad faith. Peer review starts early, long before a journal sees a draft. Internal talks play the role of rehearsal and audit. A junior member is encouraged to lead a brown bag and gets kind specific feedback. Label axes, plot residuals, show the window function of your cadence, try a different prior on thermal inertia, and remove the smoothing from your periodogram so we can see the aliases. Senior members model humility by changing their minds in public when a better fit appears, or when a systematic is uncovered. Credit is tracked. Who built the pipeline? Who pulled the all-nighter to get the calibration frames? Who spotted the background galaxy that was biasing the photometry? Because people remember fairness and because accurate authorship later depends on accurate memory now. Version control and reproducibility are habits, not slogans. Reduction scripts, configuration files, and even command histories go into repositories with tags tied to plots and slides. When a number appears in a draft, a commit hash sits next to it in a private note. If a re-reduction changes a result, the team can put two tags side by side and see exactly what lines differ. This is not just for outsiders. A month later, the same team will be outsiders to their past selves. Data releases bundle raw frames, calibration products, masks, and the list of frames excluded with reasons, so that future teams can decide differently and test the sensitivity of conclusions to those choices. Statistical discipline is a recurring theme. People ask whether a period detection survives a different detrending, whether an apparent colour change remains after removing high airmass points, whether a claim non-gravitational term still matters when the outlier night is dropped. Information criteria get computed when adding a new parameter seems tempting. A nice visual fit is not enough if the penalty for complexity outweighs the gain. Posteriors are inspected for multimodality and correlations. A narrow error bar that sits on a ridge of degeneracy is treated with suspicion. Posterior predictive checks, simulating fake data from the fit and seeing if it looks like the real data, catch overfitting that residual sums of squares miss. Communication with the outside world is paced. Press notes are drafted only when a result is robust against the obvious alternative explanations, and when the team has checked that they are not scooping collaborators or misrepresenting what is known. Jargon is translated but not diluted. We did not detect CN down to X is explained as if CN were stronger than X, we would have seen it. Hype is avoided because it backfires. The point is to keep public trust and to set expectations that scientific stories are updated as evidence grows. If a correction is needed later, the earlier note is linked and the change is explained plainly. The goal is not to be the first headline, it is to be the last correction. Ethics are woven into logistics. Telescope acknowledgements include operators and scheduling staff. Data from survey facilities are cited according to policies. Agreements with other teams about target of opportunity triggers and embargoes are honoured. When someone outside the team finds a bug or points out a bias, gratitude comes before defensiveness. The standard to aim for is, if another group had exactly our data and followed our methods as documented, they would get the same answer within uncertainties. Anything less is an invitation to confusion later. Practical constraints shape debates as much as theory does. Weather closes domes, the object's elongation shrinks and daytime sky glow eats contrast. A key night falls on a public holiday or a maintenance window. Teams have backup plans. Switch to polarimetry if clouds thin but seeing stays poor. Hand off to a smaller telescope for cadence if the large one loses a night. Cue an infrared observation at a partner facility to catch a temperature maximum when visible coverage is impossible. Flexibility is the mark of experience. The lesson is that good campaigns bank margin early so that lost nights do not sink the whole arc. The social layer matters, especially for sustaining careful work over weeks. Rotations prevent burnout on night shifts. Notes are written for future readers, not just for the current shift. Credit for tedious tasks is public. Disagreements are aimed at ideas, not people. Junior members are encouraged to say, "I don't follow," without penalty because the cost of a silent misunderstanding is high. When a result stands, authorship lists reflect real contribution rather than politics. When a result falls, the learning goes into the next plan and nobody is shamed for having explored a path that did not pan out. Finally, there is a shared sense that small words add up. Check the stars we used. Plot the residuals per site. Try a different aperture. Pull the Gaia update. Run the clones through the gap. None of these lines is dramatic, all of them keep the science on the rails. Under dim red lights, the quiet debates are not about winning. They are about reducing the space where we can fool ourselves, making each new measurement pull its weight, and leaving a trail that anyone who cares can follow from the first raw frame to the last figure in the paper, step by step, without a jump that requires trust rather than evidence. When scientists say something breaks the rules, they rarely mean nature has stopped obeying physics. They mean our current rules, the simplified models, default assumptions, and convenient shortcuts we use to predict the world, have hit their limits. In practice, rule-breaking is a signpost that points to missing terms, hidden conditions, or new regimes where the old approximations don't hold. That's not a failure. It's how progress works. Kepler's ellipses broke the circular rule of Ptolemy. Newton's gravity broke Kepler's given ellipses by explaining them. Einstein's relativity broke Newton's instantaneous pull by adding space-time, and quantum mechanics broke the classical certainty rule by replacing it with probabilities that predict experiments better. Each break retired a rule that was good enough for a while and replaced it with one that is good enough over a wider range, often reducing to the older rule in the old regime. So when an interstellar visitor seems to ignore our tidy expectations, brightness curves that don't fit, motions that need extra push, dust that behaves oddly, that tension is the exact place where we learn what to add, what to drop, and what to measure next. The value of an anomaly depends on how precisely we can state it. This looks weird is a feeling. After removing distance and phase angle trends, residual brightness rises by X% at Y degrees phase and Z hours after local noon is a target. Precision turns a mystery into a testable difference. It lets us ask whether we forgot a normal ingredient, a coma too faint to see directly, a thermal phase lag, a forward scattering surge. or whether the behaviour truly demands a new ingredient, unusual grain porosity, a strange spin state, a crust that regulates gas like a valve. If the old model cannot hit the data even after reasonable tweaks, the break has earned attention. If the data fall back into line after we upgrade calibrations, expand error bars to include systematics, or correct for viewing geometry, then the rules weren't broken, our bookkeeping was. In the background, two philosophies keep anomalies productive. The first is Popper's idea that science moves by risky predictions that could be wrong. A rule that forbids certain outcomes is more informative than one that can explain anything after the fact. The second is Bayesian updating. We start with priors, soft expectations set by past comets and asteroids. And when data arrive, we adjust our beliefs in proportion to how well each hypothesis anticipates the measurements. These are complementary. Popper tells us to stick our necks out with real predictions. Bayes tells us how much to move when the net gets tapped rather than chopped. In both frames, a crisp anomaly is gold because it changes the weight we give to competing explanations. Breaking the rules also protects us from complacency. It's easy to overlearn the last spectacular case and force the next object into the same story. A prior discovery with a thin, odd shape or a dust-rich coma can become a mental template that we apply everywhere. An anomaly jolts us out of that groove. If radiation pressure explained one object's path, but the current one shows gas lines that match the same trajectory drift, the new rule is check both, then decide. If a past object's light curve demanded tumbling, but the new one's multi-filter phase-corrected curve locks to a single period, the rule is measure, don't assume. An anomaly that contradicts our favourite narrative is especially useful because it forces a clean separation between habit and evidence. Method safeguards keep anomalies from turning into hype. First, we expand uncertainty budgets to include realistic systematics. Colour terms between object and comparison stars, catalogue zero-point shifts, seeing-dependent aperture losses, and correlated noise from atmospheric transparency. Second, we use out-of-sample tests, fit one subset of data and see if the model predicts the rest, rather than tuning to every wiggle. Third, we require converging lines of evidence, a non-gravitational acceleration accompanied by either gas signatures or dust properties consistent with a high area-to-mass ratio, a brightness-to-brightness surge that coincides with a geometry where forward scattering should spike, a period change that peaks near perihelion where jet torque is strongest. A claim that survives these filters becomes a platform for new rules, rather than a loose anecdote. Anomalies set priorities. Telescope time is scarce, so we spend it where the disagreement between model and data is largest and most informative. If the residuals align with the sun object direction, we chase gas and dust diagnostics. If they align with a long-track motion, we search for thermal re-radiation signatures. If the light curve refuses to phase at any single period, we schedule a continuous multi-longitude campaign to search for tumbling. If the colour stays stubbornly constant while brightness changes, we pivot to polarization to test grain size shifts. This is exploration-exploitation under uncertainty. Exploit what we already know to gather the most useful new data, and explore the least understood regimes to find out whether we need a new rule at all. Good rules are compact. Occam's razor is not a love of simplicity for its own sake. It's a preference for the smallest model that still explains the facts without straining. In practice, this means counting parameters and paying a penalty for each extra knob. If adding a 3-vent map on a rotating nucleus explains the non-gravitational acceleration and the observed gas production, with fewer free parameters than a speculative ultra-thin body plus exotic materials, the vent model wins. If conversely a single radiation pressure term with standard dust properties fits the path and no gas is seen despite strong limits, the high area to mass solution is the leaner one. An anomaly helps choose which side of Occam's balance to place our bet. Failures are key. When a proposed fix to an anomaly predicts a colour change that doesn't occur, or a tail kink that never appears, it shrinks the space of possibilities and saves future teams time. Documented null results, no CN to a deeper limit, no measurable P.P, no polarization swing at the expected angle, are guards against self-deception and against moving goalposts, where a hypothesis morphs to dodge each new test. In a cumulative field like comet science, these guardrails are the difference between a stack of one-off claims and a body of rules that other people can use without calling the original authors. Rule breaking also teaches humility about scale. Many rules in astronomy are approximations that average over messy microphysics. A phase function that works for most comets will fail for a surface covered in unusually fluffy aggregates. A standard gas law tied to water sublimation will miss objects driven by CO at large distances. The right response is not to discard general rules, but to map their domains. Here they hold, there they need a correction, and beyond that they fail. Each anomaly pushes a boundary marker outward, and if we keep the map up to date, the next campaign starts closer to the truth. Instruments evolve because of anomalies. A puzzling light curve motivates faster cadence and more stable photometry. An ambiguous non-gravitational term motivates better astrometry and updated star catalogues. A confusion between dust and gas bumps motivates the purchase of narrowband filters or time on an infrared facility. Even data pipelines mature in response to what surprised us last time. Automatic checks for blended background stars, improved sky modelling near the moon, and better uncertainty propagation. These are the invisible upgrades that convert an oddity today into a routine measurement tomorrow. Comparisons across cases turn single anomalies into patterns. If 3 visitors in a row show a plateau near perihelion for the same phase angle range and similar colours, plateaus stop being surprises and start being a rule with a name and a mechanism. Mantle regulation under increased solar input. If, after many objects, non-gravitational forces without gas detections remain rare and always coincide with extreme light curve amplitudes, we move thin, high-area bodies from speculation to a minority class with observed frequency. The first break opens a crack. Repetition tells us whether we've found a local quirk or a new wing of the building. Communication shapes how useful a broken rule is to everyone else. Clear statements like, "This model fails by this amount under these conditions," and "this alternative succeeds with these assumptions," let other teams plan targeted checks rather than relive our uncertainties. Overclaiming, branding every mismatch as revolutionary, erodes trust and makes real revolutions harder to recognize. Underclaiming, bearing a persistent, well-vetted discrepancy, slows the field and keeps good ideas in the shadows. The middle path is transparent. Share data, share code, show residuals, and label what is firm and what is provisional. For a sleep-friendly documentary, the take-home is simple. Anomalies are not chaos, they're coordinates. They tell us where to point the next telescope, which filters to choose, and which models to try first. They keep us honest about what we know and generous about what we don't. They are the moments when the universe taps the edge of our map and says, "Here's where your drawing is thin." Listening to that tap, measuring it carefully, and redrawing the line with steadier hands is the quiet craft behind every headline about breaking the rules, and it's how we turn surprise into understanding without ever needing the story to be louder than the evidence. When something from another star system drifts through our neighbourhood, it quietly resets our sense of scale. It reminds us that our solar system is not a sealed room but a house with doors and windows. Material goes out, material comes in. That simple fact ties our local story to a larger one and gives us a direct, measurable way to compare ourselves to distant planetary systems without going there. The practical meaning is straightforward. Each visitor is a sample carrier. Even without touching it, the light it reflects and the gases it releases carry chemical and physical fingerprints. Those fingerprints test the ideas we have about how planets form, what kinds of ices and rocks are common, and how surfaces change after long exposure to deep space. If a visitor looks normal, that supports the idea that many systems follow similar chemical recipes. If it looks odd, that tells us where our models need more room. Either result is progress because it narrows what we should expect the next time. There is also a lesson about how science actually moves. An interstellar object is the kind of event that forces many specialties to work together under time pressure. Survey teams discover and track it. Astrometrists refine its path. Photometrists read out rotation and shape clues. Spectroscopists chase faint gas lines and dust features. Modelers tie the pieces into a single story. This coordination is not glamorous, but it builds skill the way drills build a team in sports. The next event goes better because the people, the software, and the habits have already been tested. That institutional memory, how to schedule telescopes across longitudes, how to share data quickly without chaos, how to publicize a result without over-promising, becomes part of the meaning that lasts after the object has faded. These visitors make surveys and instruments better. A faint, fast target reveals where detection pipelines miss slow movers, where false positives slip through, and where calibration breaks down near the glare of the moon or the sun. Fixing those weak spots improves everything those surveys do, including the work of finding near-Earth asteroids. A target that demands polarization, thermal infrared, and narrowband gas filters motivates upgrades and cross-facility coordination that later benefit planet searches, supernova follow-up, and space weather monitoring. In this way, a single object acts like a stress test for the observing system. Passing the test is good. Failing it tells us exactly what to reinforce. There is a technology story too. If we want to do more than watch, we need ways to reach a visitor quickly. Concepts for rapid response spacecraft, interceptors that wait in a convenient orbit and sprint toward a newly discovered target, move from whiteboards to engineering plans when there is a clear scientific payoff. Even if a mission flies years from now, the work it triggers today has side benefits: faster trajectory design software, smaller and smarter instruments, more efficient propulsion stages. Those advances are not tied to one object. They spill over into other missions, from asteroid deflection tests to small probes aimed at the outer planets. The meaning here is that curiosity lays groundwork for readiness. Building the capacity to meet the unexpected makes us more capable overall. On the cultural side, interstellar visitors are easy entry points for education. They turn abstract topics, escape velocity, phase angle, radiation pressure, into concrete stories. A classroom can plot real positions, fit a simple orbit, and see how non-gravitational effects show up as small but persistent residuals. A science club can compare colour measurements from different nights and learn why calibration matters. Even a casual stargazer can grasp that interstellar means not from here. And that alone often sparks questions that lead to deeper learning. How do we know? How fast is it going? Could we ever catch one? Because the object comes and goes within a school term, the timeline matches human attention. It becomes a live event rather than a textbook chapter. There is a humility embedded in these encounters. We sometimes talk about our solar system as if it were typical, but 2 or 3 visitors are enough to show just how provisional that assumption is. If their dust is darker than ours, if their ices release at different distances, if their shapes push toward extremes, then typical expands to include more diversity. That shift matters for how we interpret exoplanet data, where we often infer composition and structure from small signals and statistical trends. A handful of direct samples, even at arm's length, anchors those inferences to reality. It keeps us from mistaking the average of what we have seen for a universal law. There is meaning for risk management as well. The same survey systems that catch interstellar objects protect Earth by cataloguing near-Earth asteroids. Every improvement in cadence, sensitivity, linking algorithms, and follow-up logistics prompted by a fleeting visitor pays a dividend in planetary defense. The math and software that keep a fast mover in view at small solar elongations are the same tools that help us track a newly found potentially hazardous object during its critical first nights. In this sense, basic research and safety are not separate lanes. They share the same road and improve together. Ethically, these objects challenge us to handle attention responsibly. They are perfect vehicles for hype. You can say from another star system, and be technically right while implying mysteries that aren't there. The better path is to model how to be excited and careful at the same time. Show the data, show the uncertainties, explain what would change our minds, and update the story when better measurements arrive. Doing that in public builds trust not just for this topic, but for science more broadly. It teaches that changing your conclusion when the evidence changes is not weakness. It is the core of the method. There is also a simple human comfort in the timescales involved. An object may have drifted for millions of years before crossing our sky. Our telescopes watch it for weeks. We think about it for months. That mismatch is not discouraging, it is grounding. It reminds us that learning is often a snapshot taken from a moving train. We do not control the timing or the angle, we control how carefully we look and how honestly we write down what we saw. That mindset applies beyond astronomy. To climate measurements, to medical trials, to any field where we observe a small piece of a larger process and must build understanding from partial views. For people who like practical takeaways, a short list is clear. Keep investing in wide-field surveys because they turn rare events into recurring opportunities. Build flexible follow-up networks so that when a target appears, instruments with different strengths can act like a single distributed observatory. Share data and code when possible so independent checks can happen quickly. Train students on real-time campaigns so they learn how to plan, calibrate, and communicate under pressure. And when the event ends, write down what worked and what did not so the next team starts a step ahead. None of these points depends on a specific object, and all of them leave the community stronger. Finally, there is a quiet philosophical note that is easy to miss because it does not shout. An interstellar visitor does not prove we are small, it shows we are connected. The same physics that shapes dust near a distant star shapes dust here. The same chemistry that locks water and carbon into ices out there releases them in our sunlight. The same methods we use to make sense of our comets work, with adjustments on travellers from elsewhere. That continuity is the most durable meaning, a reminder that the universe is not a set of sealed compartments, but a continuous field where local knowledge scales outward, if we are patient and precise, and where each passing fragment can be enough to tie our small, brief observations to very large, very long stories without needing to make them louder than they are. The sky grows quieter when we learn how to listen to it. Not because the stars stop burning or the wind from the sun stops flowing, but because our attention begins to move with steadier breaths. A small object from elsewhere slides across our instruments and across our thoughts, and the pace of watching slows us down in a good way. Numbers arrive like footsteps on soft ground. Time, brightness, angle, position. And with each careful step the picture sharpens without needing to rush. Somewhere between the first faint detection and the last useful frame, curiosity becomes a rhythm. Telescopes rotate, domes open and close, detectors cool and warm, files fill and queue, and people trade shifts the way long-distance runners pass a relay. The object does what it will do. We adjust our expectations instead of demanding a show. That simple adjustment is its own kind of kindness, a way of meeting the universe where it is. There is a comfort in small scales. This traveller is not a planet, not a ship, not a threat. It is a piece of something that formed far away, comparable in size to a neighbourhood hill or a city block, turning in space with no audience until we happen to notice. The light we measure left the sun a few minutes ago, kissed that surface, and reached us a few minutes later. The delay is short enough to feel immediate and long enough to remind us that everything we see is slightly in the past. When brightness rises a little and then eases, the cause is already over. When a subtle push changes the path, the jets that did it have already relaxed. Accepting that lag is part of the calm. We do not have to catch each moment at the exact instant it happens. We can let the signal come, measure it cleanly, and let the meaning settle over hours instead of seconds. As the object fades, the work changes shape but does not stop. Observers write up logs with the same care they used on the hardest nights. Pipelines that were tuned in a hurry, get polished so that the next campaign starts smooth. Draft figures are saved, then redrawn with clearer axes and quieter colours. People who learned how to phase a difficult light curve teach the trick to someone who hasn't tried it yet. A list grows of ideas to test when the next visitor appears. A better script for handling phase angle corrections, a gentler way to combine polarization from different filters, a template for sharing data that is easier for outside teams to adopt. None of this is dramatic, and all of it makes the next Quiet Watch easier. The object itself keeps going. Past our orbit, past the slow hills of the outer planet's paths, back into the sparser sunlight where the coma thins and thermal light drops into the noise. The non-gravitational terms we work so hard to measure fade into the background. Gravity resumes its near monopoly. Our models need fewer small corrections. There is a certain beauty in that, as if the traveller and the sun negotiated a truce that gets simpler with distance. We plot the last points, extend the line with appropriate uncertainty, and recognise that most of the unknowns no longer matter to navigation. They matter to understanding, and understanding can keep going long after data stop. That is the promise of analysis. To let a short visit continue as a longer lesson. Sleep comes easier when a problem is well framed. The questions we could not answer tonight are written down clearly. How fast did the spin rate change? How strong were the smallest grains in the coma? Did the plateau near perihelion reflect mantle growth or simply geometry? Each question sits with its references, figures, nights, file names, so that picking it up tomorrow will not require starting over. The mind has something trustworthy to return to. Outside the windows, the sky is doing what it always does, rotating, dimming, clearing, clouding. Inside, time slows enough to feel the difference between hurry and focus. There is a kind of quiet that data work gives you when the goal is accuracy rather than victory. It is not dull. It is steady. If you step back from the details, phase functions and AFREO and beta curves, you can see how much of this practice is simply learning to separate what changes fast from what changes slow. The fast changes are rotation, jet sputters, little kinks in a tail as the solar wind shifts. The slow changes are shape, pole direction, crust thickness, overall volatile inventory. Knowing which is which makes decisions easier. Observe quickly for the fast, schedule steadily for the slow. The same habit helps outside of astronomy too. Some things ask for patience. Some things ask for presence. Most ask for both in proportion. A small visitor teaches this without preaching it. You either match its time scales or you miss the truth of it. There is pleasure in being part of a chain of care. A discovery alert pings, someone confirms, someone else posts ephemerides. A student grabs the first photometry. A survey contributes astrometry. Another group adds a spectrum. A small telescope supplies a long, clean run that turns out to be the anchor for the period. A larger facility gets one night of thermal IR and breaks the size albedo tie. The orbit modeler threads the points into a path with uncertainties that are honest. A writer turns the jargon into clear sentences for the record. No single step is sufficient and none is wasted. The object moves on, but the chain stays ready, stronger for having just been used. Even the words we use change tone after a while. In the beginning everything is weird, or unexpected. With enough measurements, words like consistent, stable, and within limits start to take over. That is not a loss of wonder. It is the arrival of understanding. The quiet language of consistency is how we tell ourselves that we are not simply making patterns out of noise. It is how we store a result in a way that the next team can find it and trust it. When we switch to that language, we are not deflating the story. We are making sure it can be retold without us present to defend it. If you find yourself outside at night while one of these campaigns is running, it helps to look for the simplest things. The moon, if it is up, and how its glare changes the sky. The bright planets, if they happen to be in season, moving so slowly that only last month's memory tells the difference. The strip of the Milky Way when the air is dry and clear, reminding you that most of the galaxy is soft light, not sharp points. Somewhere among those points is the path our visitor took. You cannot see it with your eyes, but you can hold in mind that it exists and that people are marking it, gently and carefully, with tools whose only aim is to notice without disturbing. That is enough to make the night feel larger and more patient. The object's name will fade into a catalogue full of names that most people will never read. That is normal and fine. What will remain useful are the habits it sharpened. Start simple, correct for geometry, check for systematics. Prefer small models that fit before large models that explain, keep uncertainties visible. Share methods, be ready to change your mind. Those habits are portable. They work on bright comets and faint asteroids, on spectra and light curves, on old data sets and new ones. They work, with translation, in any field that tries to turn careful observation into reliable knowledge. Carrying them forward is a way to honour a thing that will never know we looked at it. The feelings that gather around a campaign do not need big words. Relief when a tricky calibration finally behaves. Gratitude when a stranger on another continent grabs a gap night and nails the coverage. Amusement when a period alias that fooled everyone for a week collapses with one long run. A small pride in a plot where the residuals sit close and quiet around zero. None of these makes news, and all of them make the work worth doing. They are the human texture that science journals don't print, but that lives in lab notebooks and shift logs, and the memory of people who like their nights slow and their uncertainties shrinking. By the time the last frames are taken and the last tables are checked, the object is far enough that its light will not help us much more. That is all right. We have the arcs we need, the curves we can defend, the stories we can tell without reaching. If more is needed, it will be needed by the next object, and now we know a little better how to meet it. Instruments will be cleaned and cooled again. Scripts will be archived with clearer comments. A few new students will have learned how to steer a telescope, how to respect error bars, how to present a result without leaning on adjectives. The sky will have another small mark in our records and will be no different for having been observed. We, however, will be slightly different, quieter in our claims, quicker in our checks, steadier in our attention, and more practiced at the kind of looking that lets sleep and knowledge share the same slow breath. If your eyes feel heavy now, that is okay. Let them close if they want to. The sky will keep going without us for a while. 3-Eye Atlas will keep moving too, a quiet traveller sliding back into the dark between the stars, following a line we measured for a short time and then gave back to the night. You do not need to hold the numbers anymore. You do not need to remember the terms. Just keep the simple picture. A small guest from far away passed by, and we noticed gently, with care, and with enough patience to learn something true. Before we say good night, take one slow breath in and one slow breath out. Think of the way light took minutes to travel from the sun to the object and then to us. Think of the way the telescopes turned with quiet motors, the domes opened, the instruments cooled, and people traded shifts so the watch could continue while you rested. Science can be loud in headlines, but most of the time it sounds like this: a soft hum, keys pressed slowly, a pencil tapping a notebook, a whisper to a teammate to check one more thing. That is the sound you're hearing now, steady and calm and unhurried. If tonight left you with the feeling that the universe is large and patient, let that feeling stay. If it left you with the sense that small details matter, the phase angle written on a plot, the way dust forward scatters light, the careful subtraction of a background star, that is good too. Those small details are how we meet something as big as interstellar space without getting lost. We carry a small lamp and write down what we see. The lamp does not have to light everything. It is enough that it lights our next step. Let your shoulders drop. Let your jaw unclench. Imagine the object now as a faint pinhead, farther away with every heartbeat, leaving behind only a neat file of measurements, a few graphs, and a line in a catalogue with a date and a set of uncertainties. That is all most things in science become in the end, a clear record someone else can read and trust. That is not sham. It is a generous way to let knowledge live longer than our attention span. If you are still awake, you can rest your thoughts on a slow list of simple truths. Gravity still curves paths, sunlight still pushes a little, ice still turns to gas when warmed, dust still carries memory in its colour and polarization, magnetic fields still drape around outflows like ribbons in a stream, instruments still need calibration, error bars still matter. We don't know yet is still a good sentence. Consistent with is still a kind sentence. These truths do not ask for effort. They sit like small stones in a pocket, smooth and familiar. If you want company as you drift off, picture the wide field survey scanning at their measured pace, a strip of sky each night, a new set of tiny dots. The computers compare, the flags go up, human eyes look, and once in a rare while something that was not here yesterday is here today. There is no rush in this picture. There is only cadence. Cadence is a friendly word. It means we can be present without hurrying. It means we can return tomorrow and pick up where we left off. If your mind picks up a question, what if the next visitor is brighter? What if it shows gas earlier? What if it tumbles differently? Let the question float. Questions do not need to be answered right now. They can wait on a clean page. The best questions prefer waiting. When you wake, the page will still be there. The sky will still be there. The next line in the story will wait for you to write it carefully. If you found some peace in the way careful work replaces noise with signal, take that feeling into the rest of your night. The same habit works for worries and plans. Subtract what is only glare. Keep what repeats. Trust the slow patterns more than the sudden spikes. Check your assumptions. Leave a margin for uncertainty. Share your methods with people you trust. None of this is only for telescopes. Thank you for spending this time here, for letting a very small object and a very large sky be your company. If you want more quiet stories like this, where wonder and care share the same space, you can subscribe and turn on the bell so future episodes find you gently. You can leave a simple comment. What part helped you breathe slower? What part made you curious? And I will read it. You can share this with someone who needs a soft edge to their evening or a calm start to their morning. These are small actions, but they keep this channel's light steady so I can keep making this kind of calm. In the minutes after this ends, you can let the room dim even more, let the screen go dark. Hear the small sounds around you, a distant car, a soft vent, your own breath. The universe is loud somewhere else inside stars, in the shock fronts of solar storms, in the collision of dust grains. But here, now, it can be quiet. That quiet is not empty. It is full of everything we did not rush, full of the patience that lets sleep arrive the way a new detection arrives, slowly, clearly at the right time. If sleep is already here, you don't need to follow this to the end. If you're still with me, we will close with an image that you can keep. A dark sky, a faint path arcing through it, and a small circle drawn in pencil where we last saw the traveller. Next to the circle a note, seen, measured, shared. That is enough. When your eyes open again, there will be new circles to draw and new notes to write, and the same careful attention you practiced tonight will be ready for them. Until then, let the last of the music fade. Let the credits roll in your mind like quiet constellations, and let your breathing match the long rhythm of the night. May the questions wait for you patiently. May the answers come in their time. May the space between them be soft and generous. Sleep well, traveller under this sky, and thank you for watching.